Okay, first of all, thank you very much, Mr. Gülçer, for your beautiful speech. Now I'd like to present our first speaker, Uğur Tanrıverdi. He is Imperial graduate in 2018 and currently a bioengineering PhD candidate and co-founded Unhindered. Now we would like to hear the present. The participants can ask the questions below the chat part. We are going to take the questions after the presentation. I hand the word over to you, Mr. Tanrıverdi. Thank you.
Thank you very much, Hilal. And good morning, everyone, once again. My name is Uğur. It means good luck in Turkish, as most of you would know. Today, I'm going to show you some of my findings during my Master of Research and PhD research. Just let me allow to share my screen quickly. There you go. Okay. Hope you can see my screen. I think so. So today I will talk about around 30 to 40 minutes about soft robotics and their practical applications in medical devices, in the field of medical devices, particularly in prosthetic liners. You don't need to do anything, just relax and listen to me, take notes, and please ask me questions when the presentation finishes. That's how I feel my research. So a bit about me, first of all, before starting. I've studied biomedical engineering at Yeditepe University in Istanbul and graduated in 2013 with honors degree. And then I moved to London in 2014 to study my first master's in advanced engineering design, where I designed a prosthetic system, an upper limb prosthetic system, actuated by shape memory alloys. And after that, I set up an engineering consultancy company, but that wasn't enough for my research career. So I applied for a second master's at Imperial College London for medical device design and entrepreneurship. That's where this research, the one that I will just show you, came up as an idea, and that's how it started to grow legs and arms from there. And after that, I set up a second company for that. I will briefly mention in the end of this presentation. And that became the foundation to my PhD research, which I'm currently undertaking at Imperial College London. So today's topic is, as I said, prosthetic liners. Before that, I would like to give a couple of facts about prosthetics and what prosthetics users are going through. So the problem is, this is called a prosthetic socket. It is non-adaptive. It's made of a solid shell. It's usually thermoplastics they're made of, or composite materials like carbon fiber. Not flexible. It has to be rigid, made from the hard material so that it can carry the body weight and it can endure to the large gate forces. And because everybody has a unique body shape, all of these devices are handmade, and it takes around a week to form those. And what people are doing to make sure they are they're better fitted, they distribute the pressure better, they're trying to understand the pressure mapping, because the function of the socket, it has to connect the limb, attach the limb to the body. B, it has to distribute the body weight on the internal surface so that the skin is not going to get damaged. The problem is there, after the amputation, the leg skin becomes vulnerable to pressure because the leg skin hasn't evolved to bear pressure. For example, on the other hand, the foot sole, as you start running on walking, you can run barefoot or you can walk barefoot. It's not gonna bleed, because although it is so sensitive that you can even sense a feather under your foot, it is also so structurally robust and extremely well pressure distributor that you don't get pressure source. On the other hand, leg tissue it takes over the job of the foot. So after the amputation, it has to distribute the pressure all around the ring. However, since it's a very thin and delicate skin, in any constant applied pressure over a long time, it starts getting pressure source. And that's why researchers are looking into pressure mapping to distribute the pressure, to take it away from the areas where the pressure can accumulate and break the skin. They are developing software packages for design processes. Most of these are 3D scanners. So they are scanning the residual limb of the patient, and then they are looking into how we can create a geometry around this, again, custom made, to allow the leg to have a bit of space if there is any friction, any pressure, so a pressure accumulation happens. And also the last one, which is the most recent development, is adaptive pneumatic sockets. So this is basically, they are introducing some dynamic systems inside of the socket surface. And these interfaces, dynamic interfaces, are in charge of distributing the pressure and changing their geometry and shape when it is desired. However, there is a drawback on the pneumatic sockets. I will explain about that shortly as well. While academia looks into these kind of aspects, the clinical practice is way primitive. When there is a pressure source, pressure sore, or pressure ulcer problem, the clinics are either replacing the socket with a new one, which is going to cause the exact same problem, or they're adjusting it, which means they're locally heating it and they're changing its geometry so that it's going to be a new custom-made, locally changed geometry. Or they are giving the patients, amputees, extra layers. As you can see, it's cotton socks. They have different thicknesses with open end. They wear extra layers, 1, 2, 3 layers, to just change the thickness of the size of the leg. And in some cases, this thickness can create the padding. But what I am aiming to do is, without doing pressure mapping, without using an expensive software, or without using adaptive sockets, so like throwing the old socket and getting an adaptive socket, or replacing the socket, or adding extra layers, I'm developing one layer, which is there. You can see the green layer. It's called a prosthetic liner. This is already something amputees uses for comfort. So instead of using a normal liner, I am questioning, what if we make an adaptive liner that can do the pressure mapping, that can change its shape and geometry as the amputee wants, and it will eliminate the socket replacement because the socket will be constantly adjusted from inside. And also the socket doesn't, and a new socket doesn't need to be made for this. It will work with the existing sockets. So in healthcare, this is very important, because if you have a system that requires training, the training of the healthcare staff, it becomes very expensive. So if it is going to be a translational research, you always have to think about how you can integrate this piece of work into the existing supply chain with minimum training, minimum change in the system. And this is where this research comes in play, because adaptive sockets, they use some robotic interfaces, but people who are making the sockets at the hospital are just crafts makers. They don't have electronics, background. So retraining and redeploying all of that stuff is where the problem starts. And with these overall, when you look at it, today, what I'm covering is an adaptive user controlled fitting, thanks to this liner, prevention of those chronic wounds, because as I was explaining, the leg tissue is not as robust, as resilient as the sole tissue. So if we can distribute the pressure over the time, all the time, not only with one shape, but with a dynamic shape, then we can actually prevent these chronic wounds appearing. And ergo, you would save time and money. So, prosthetic limb fitting. The problem is that it is prosthetic limb is not fitting. And this problem has been existed since 19th century. So on the movies, you see that there are people wearing robotic joints, or even in some sci-fi movies, you see like robotic people. Unfortunately, the reality is, yes, we have cutting edge robotic joints like knee joint and ankle joint. However, when it comes to the fitting, which is the attachment of this expensive piece, the attachment of this into the human body, unfortunately, it still uses 19th century. So this is the big technology gap that prosthetic limb users are facing at the moment, because it doesn't matter how delicate, how sophisticated system you are using. If it is not your size, if it is not fitting, you just simply cannot use it. This is explaining with an analogy. This is how I usually explain. You have an expensive pair of shoes, I don't know, you name it, Prada shoes, but they are not your size. So you're gifted them, it is yours. But let's say you even didn't pay for it, the healthcare in that case gives them. You're gifted, you're given them, but they're not your size. You simply won't be able to wear, or if you wear it, there will be consequences where it will hurt. So this is the day-to-day problem of prosthetics. The real reason behind this is because human body change shape throughout the day, but prosthetic fittings don't. So we are 1.5 centimeters shorter in the evenings compared to the mornings because of gravity. Or our feet and hands are larger in the evenings. Most of us don't notice these changes because we wear flexible clothes, which is just logical. But when you lose a limb, they give you something that is not flexible, and that's where the problem is starting. So this is an amputee, Peter. Peter wears his socket in the morning. A few hours later, his body changes shape, and then it starts hurting because it either rubs on the skin because it comes loose and starts rotating and rubbing, or it starts squeezing the leg, applying extra pressure to a very vulnerable tissue. And then he goes to hospital for adjustments, but these adjustments are just temporary. Eventually, the pain comes back after the adjustment, and which is around one week. And the pressure breaks the skin, and he goes back to his wheelchair to wait for the new sockets to be made. And these new sockets are gonna cause the exact same problem. This cycle repeats up to 4 times in a year. And unfortunately, Peter is not the only one. Every year, 300,000 people in the US and EU and also UK are losing a part of their limb, majorly due to diabetes. And 3 out of 4 amputees are unhappy with their prosthetics. And if you think about in the medical record and history, this is an extreme patient discomfort, dissatisfaction rate. And the result of dissatisfaction is it costs annually 5 billion euros in the US and UK alone to just keep these sockets fitted. Sorry to show you in the early morning, when I say it doesn't fit and it traumatizes the skin, this is what it does. This is not because of amputation. This is when the pressure accumulates on the skin, it starts breaking the skin, and eventually it causes pressure sores and then pressure ulcers. Most of people, as I said, lose their leg because of diabetes, and those people don't have ability to heal the chronic wounds. and therefore these wounds become basically infected, and then that infection goes into the further deep tissue and goes to the bone, and then that requires a secondary amputation. So it is not only the comfort, but also it is a medical requirement to prevent a medical complex medical issues. In the literature, I briefly explained it, but in detail, what is happening is, so one thing they're trying to do, they're trying to look into how this pressure distributed all around the socket. And this socket is, for example, a below knee socket where the kneecap is right there. The pressure points are shown with the arrows. So what they do is, based on this, the number one is the side view of the leg, where you can see the kneecap right at the top. And the other one is the frontal view. The second one is the frontal view. So this is called patellar tendon bearing socket. If you look at number one, there is a curvature there, and that curvature is accommodating the patella bone, which when you wear it, it just embraces, hugs the patella, and that's where the socket is basically fitting into the leg. And then the rest of the geometry is distributing the stress. With that, they also tried introducing some different textured socket shapes so that they would increase the friction, and they would change the horizontal spacing. Horizontal spacing is the one, so if you think about the socket is this long, if you think about that, when you increase the length of the, when you increase the surface of the surface friction of the socket, you increase the surface area. So that, as a result, can create a larger suspension force to keep the limb attached. But the problem is, as you increase the surface roughness, then if there is a rubbing happening, that is gonna break the skin even easier, because it's a rough, even rough surface. The other one is an adaptive socket. This is a very basic pneumatic system with a reservoir, with a pump, and display some inputs and outputs. What it does is it inflates within the socket and compensates the gap. This is very similar to my research, Roliner, but the problem here is these devices, so sockets, they get dirty, so they need to be cleaned. When you introduce electronics into them, cleaning of the socket becomes, first of all, harder. Second of all, this is a wearable device, and if you can look into the schematic, there is a pump. Wherever there is a pump and valve, there is energy requirement, because you have to compress the gas, you have to pump the air or fluid into the reservoir, and in that case, you need the battery. So battery consumption of these kind of devices is so high that, as a wearable device, if you wear it in the morning, in 3-4 hours, you will be out of battery. So you have to recharge it. And also, batteries are very heavy, and that is where the problem also plugs in, because these people require 70% more energy to walk, because they lost a joint, at least a joint, and some muscle groups. So when you have less muscle but more energy required to walk, then anything you add as an extra becomes a problem. And the third one, as I was saying, is the integration of these systems into the healthcare systems, because these systems are complex for healthcare staff to understand, to train the patients for usage, and they don't work with the existing socket designs. The other one is a smart liner controlled by muscle activation feedback. But this is basically trying to create some dynamic suspension underneath. But it's also with user control. And what they're trying to do is they're using electrodes on the surface. So what it means, you just take this as you walk, depending on the gait cycle of your leg and the muscle activity, the system starts actuating itself automatically, which is not really the ideal case, because if you have electrodes, as I was telling you, it needs to be washable system. So theoretically, yes, it works, but in practice, it doesn't meet the design requirements of an amputee, because this needs to be washed. And if you introduce electronics into that on the surface, that is going to cause problems when you try to clean it. So soft robotics is another approach, which is the inspiration of my approach. So we have a soft robotic video here. This is a very classic one, but I like because it explains everything. So this is made of, this is a microfluidic device. Maybe not microfluidic, but it's a macrofluidic device. Maybe I can just, okay, it's already silent. By actuating different sides of the chambers zones, you can actually change its geometry, and therefore you can manipulate the device. So I was thinking about these when I was doing the masters. These are extremely adaptive, they're light, and they don't necessarily require precision, because wherever you have precision, that's where the high cost of manufacturing relies. Rubber silicone manufacturing is very easy. It's also used in handcrafting and hobby and leisure time activities. So this was the beginning of the idea, because, okay, the video is about to finish, but let's watch the whole video that this little guy is passing through that glass panel. And there you go, it passed. So this was the starting point, and you can search this on YouTube. There are lots of different other videos. They've done octopus and some other devices, bio-inspired devices, and they're used in wearable robotics, such as exoskeletons. So these things form a wearable piece, I wouldn't say clothing, but a wearable device, and when you actuate them, they start exerting force on the body. So depending on if you, let's say, have a knee injury or any other joint injury, the force generated by these structures are offloading the load at the joints and helping your rehabilitation, or if you have any muscle problems. But also they have, although I don't like it, they have military defense applications where exoskeletons are used for the member of militaries, so soldiers, so that they can carry more weight, because some of the weight will be carried by the exoskeletons wearable robotics. So instead of carrying 20 kilos on their backpack, they can carry 40 kilos on their backpacks. So there are defense industry applications as well. But as a scientist, I prefer to focus on things that will make a difference to human life in a nice way, not in a negative way. So the design thinking was, soft robots are made of elastomers and they can conform to uneven shapes. Prosthetic liners are made of elastomers and required to conform the shape of the leg for a sufficient limb fitting. A soft robotic liner, therefore, could improve the fitting performance and comfort. So this was the beginning thinking, because it would require the minimum transition effect, minimum impact on the healthcare services in terms of adaptation, but it would have the maximum impact in terms of prevention of medical issues. So the solution was a silicone layer with microfluidic channels inside, like tiny air bubbles. When the leg expands or when the leg shrinks, the air pressure of the bubble changes, and then an AI algorithm understands these changes to adapt to them automatically so that it will prevent the pressure source. And what is different here than the device that you have, the device that I've shown, is that we use we use compressed air canisters. So we use carbon dioxide canisters. They're right at the right bottom of the screen. These have 900 psi compressed air inside. It's an enormous force. Compare this side, a car tire is around 32 psi when it inflates. This has 900 psi inside. So it's extremely high pressure, which works in this sense. You don't really have to energize the system with a pump. You can just use a pre-energized gas, release it into the system, release it into the microchannels, and then only control the system by using a valve and a sensor. And these are very low power devices, so components. The valve opens and closes in 3 milliseconds, the valves that we are using, and the sensors are very low cost in power consumption as well. So by having these disposable cartridges, you get rid of the weight problem because each of these have 16 gram carbon dioxide inside. You get rid of the weight problem, you get rid of the battery problem, because the battery, the prototype we have developed, the battery lasts around 6 days instead of 3 hours. But also the last thing is, because this is a compressed air, the compression of the gases, speaking of thermofluidics and thermodynamics, results in temperature drop of the gas. And we all witness this every day almost from deodorant bottles. When you start spraying, the bottle gets colder. That can be an advantage in this setup, because when the gas decompresses, the temperature of the gas drops, and this cool gas starts circulating around the leg to cool the leg. The other problem that amputees are severely complaining is the sweat and heat problem. Because it's an enclosed system inside of the socket, sweat becomes a big problem. First of all, it makes surface more slippery, but also because of the skin oils and the sweat electrolytes and acidity, it makes the skin break even easier. And also it's a perfect environment for a bacterial feast. So infection will be almost inevitable. If we can reduce the sweating and heat by circulating a cool gas around the chambers, that will be just a double achievement. So with this system, what we want to achieve is a dynamic suspension system and a remote pressure mapping. So we don't use any electronics on the liner itself. We connect the liners via tubes we connect the pneumatic cell structure via tubes into a control box, where this control box is just attachable to the socket outside. So you can wash the liner even if you want in washing machine, it's not going to cause any problems. And the box, which is remotely connected to the liner's different zones, that is doing the pressure mapping. And wherever there is a control and electronics, there is always a mobile app now these days. So there is a mobile app, and this app is allowing the users to change its socket, its fitting, geometry, tightness. But moreover, the smart control box is connected to the phone and connects also health data from the phone. And the phone also connects the data like gyroscope, accelerometer, and step count data from the device, from the box. So thanks to this, we can tell how many steps they walk in a day. We can look into what is their average speed of walking. And after amputation, their body becomes asymmetric. So when there is an asymmetry, it is over a long term, prolonged term. This is a problem for joint health. Most of amputees faces hip joint problems because they have to walk in a different way than the hip joint was designed. So the physiotherapists are trying to encourage them to walk on a straight line, but unfortunately they have to swing their legs more to be able to catch with the same speed. And all of these swing motions can be detected by Rolliner. So we can give them insights that, let's say you walked 55% centered this week. So better, let's say 20% better than last week, but you're still not there. So it can be a rehabilitation tool. It can prevent the wounds. But lastly, um, for manufacturing wise and environmental thinking, because this whole plastic, thermoplastic thing is around 3 kilos. So when you change, sorry, around 1.5, 2 kilos, when you throw it away to replace it, it's a medical waste also. You cannot recycle it. There is so much plastic for environmental pollution, but in this setup, you can extend the life of that plastic, but also this type of manufacturing, like soft robotics, I was showing you the video, is also suitable for conventional manufacturing. So the next step into this idea was proving the concept, actually, how it would work. So this shoe insole is inside of the shoe. And as the person starts walking, you can see the peaks there. I will stop here so that I can show you. The peaks, the top part is, as you can see, slightly delayed than the bottom part, because the bottom is the sole of the feet, which touches the ground first. So that's why the gate pressure reaction occurs the first one. And the second one is the pressure of the toes. You can see on the left top corner of the screen that there are two zones. So the bottom one is coming from bottom, the top one is coming from there. And you can actually see it's a bit like the PQRST wave. There is a characteristic on how the person walks, because gait analysis, like fingerprint, facial recognition, iris recognition, gait is also a biometric data. You cannot mimic someone's gait. So this biometric data can be used to be characterized for that person to understand their gait pressure pattern and then suggest them a fitting, a unique fitting. So this was the first proof of concept, because it was easier to do it on able bodies, because the liner needs to be thin enough so that it can fit into the socket. So when we get to the fabrication stage, it's silicone, as I was saying, inexpensive, very good, but if you want to do complex geometries, that is a really pain in the back part, and it's very sticky. So I got this leg mold from St. George's Hospital. It's the leg measurement of an amputee. And then with the first basic simple design mold, it a bit looks like ice cube molds. I just cured one bottom actuator and then turned that actuator in C upside down in a pool of uncured silicone, like this. Basically, I took it and I turned it upside down, dip it into silicone. When that silicone when that silicone cured, it became a whole one structure, and then I deployed it on with 90 degrees on top of that fixture. That fixture went into the mold this way, and there is on figure D, there is the gap in between, and that gap is then filled with silicone and let it cure, and then voila, you get the um, you get the liner. So here, by the way, this is what I designed on the computer, figure G, and F was the result. So it was spot on design. However, there were some problems. I will come there. So I made 11 soft robotic liners with 2 actuators, 3 actuators, 4 actuators, and I use low surface tension. So I use something called surface tension diffuser to get rid of the stickiness of the silicone. So it became a very smooth silicone. surface, um, which is great for the skin contact. And then there was the design validation. So this is basically to see how much force it can generate, but also can it, when you do cyclic test, can it actually stays integrated as well? So there was a setup here, which is there is a tensile machine, material testing machine, McMesson 5XT in this case. Then you have the load cell, the grip head, that is connected to the inside green part. And the green part plays the role of a leg. So the machine pulls the green part, which means the machine is pulling the leg up, and then the liner is actuated and applying pressure onto the leg. The the the purpose of this, this is back in 2017. So this was the first experiments we were doing. The idea here was, can it generate enough force so that it can keep this in place? And it turned out, actually, with full actuators, full actuation, which is 40 milliliter air per actuator, it almost reaches to 250 Newton, which is roughly 25 kilograms. And one prosthetic socket, below knee prosthetic socket, is around 3.5 kilos. So we reach more than the required 35 Newton versus 250 Newton. So we managed to reach to more than required threshold to keep it fitted. And obviously here there is also another thing. No actuation, like the liner itself, like a basic liner, is around 50 Newton. So you can see when you actuate it, there is a significant suspension force generated. And that suspension force is characterized, the more actuators you have, the more actuation you do, the maximum you go. So we wanted to achieve full actuation. But when I showed these to amputees, they said, "No, I'm not gonna wear this." I said, "Why?" Because it is so thick. So I'm barely wearing my shorts and jeans during the day. If I wear this, I won't be able to wear my shorts and jeans, and I would be rather wearing my own socket and wear the clothes, at least the clothes I like, and feel more confident, rather than wearing something that's going to make me change my clothes as well. And this is where you have to think about as a design engineer. You can design something, and this is where that part of the research that I was showing you was lacking. You can design whatever you want, but if your user is not going to like it, it could be an engineering marvel, but if your users are not, or end users are not going to like it, it simply won't be a success. An example to this is um, the airplane A3, the Airbus A380s, massive double-decker airplane, one of the most sophisticated airplanes in civil aviation history, yet it didn't meet the need of the airlines, and that's why Airbus stopped its production now. So it doesn't matter if you make planes or rockets, if you're not meeting the user requirements need necessarily, don't push it too much. So when we did these human subject trials, first we tried on able bodies by just cutting the open bit to see how much force it is exerting. That 250 Newton, is it really hard to bear on the skin, or is it more comfortable? We did some trials with some amputees to see how is the skin reaction. We used medical grade medical grade silicone, but the feedback was the same. It's too thick and there is loss of control. So the more the gap between the leg and the socket increases, the less control they get over their prosthetics. Then we started to look into a different version where we can fabricate it. And this method of fabrication, open flap fabrication, happened as an accident. I just opened, it didn't work, and I got angry. I just tore it and threw it on the floor. And it just opened and stayed like that. And that gave me an idea. Why don't we do this as a flat liner first and then roll it closed instead of making it closed liner? It failed. So it was gonna have a thinner wall and lighter design and more actuators in it, but as you can see, the connections in between are blocked. And then I invented a new method. This is basically what we have been using. So bear with me. I know I've talked too much, but this is basically the part that is enabling a wearable device. Roliner being a light and robust wearable device. So on A, you have the cross section of the mold, and that could be any shape, as you can see on that. And then you pour silicone on it, let it semi-cure. Semi-cure means it is solid enough to pull it, so it's not liquid anymore. It's solid enough to pour it, but still in chemical level, there is cross-linking happening. You turn it upside down, put it in a slightly larger mold in C, and then you fill the channel with water, and then you pour additional water, additional silicone on it, and because the cross-linking of the bottom layer is still going on, it cross-links to the top uncured, and then you get a channel from one block of silicone rubber. And by just using empty air, you can just blow the water out. I have done a shape like this, S-bend rectangular footprint. Like that just made things way easier for precision, because you can exactly arrange where the channel is going to be instead of taking it down and putting it by hand. And the channel could be very thin. And this was one of the results I've made. One of the samples I made, the first microfluidic in this setup. So there is an ink circulating inside of it. And this channel was 2 millimeter in diameter. So it was very promising. Then I tried lots of different geometries to see which one is going to work, and then apply that into a closed liner shape. So on this one, right top, I explained what is it. On the second image, it is an amputee wearing the liner. That liner has the microfluidic channels inside. And in the challenge and approach part, what we were trying to achieve is the actual thickness of the liner is now 6 millimeter. So this is basically thanks to that bottom layer and then the top layer poured by the poured the uncured silicone poured, and we can get the skin feel like silicone at the bottom and at the top, so that when it touches the skin, you don't get that. The key here was freezing the water. So because there is surface tension of the water, in any complex form, if you pour silicone from one end, the weight of the silicone is going to dig into the channel and it will pop up in the other of the channel. The water will pop up on the other end of the channel. So in the literature, people are using some dissolvable materials, 3D printed filaments like PVA. However, if your channel is too long and too complex, you won't be able to dissolve your sacrificial layer. So this is the method that I've developed. Instead of using a sacrificial material that is like a solid, why don't we use it as water, freeze it, make it solid, pour the silicone. Once silicone is completely covering all the area, the ice dissolves and silicone applies equal forces onto the onto water, and there is no surface tension or weak point where the water can pop up. And that worked really well. So what we did is we used EcoFlex for silicone rubber. It's a medical grade silicone rubber. Then the problem became the top layer and the bottom layer had to completely cross-link. So this was because although the bottom layer was semi-cured, we had to characterize when to take it off, but when to demold it so that it will have enough cross-linking in silicon, basically can make connections with cured silicon, platinum cured silicon, um, then you would get a robust screen. You would get a robust structure. For that, it turned to be somewhere in the middle, which is now, we know it is 35 minutes at 40 degrees, 40 Celsius degrees. That is the perfect timing for the first layer to be taken out of the mold and merge with the second layer. The next stage was, because I was talking about how to make this handy and production-wise, like scalable thing. Now we introduced a problem. The total channel length is 4 meters, like more than 4 meters, and it is 0.95 millimeter diameter, thanks to this method. So on the right side of the screen, where you can see two photos, there I developed a device that is a plotter actually, but it purges water. And at the bottom, there is minus 24 degrees, basically cold steel platform. So this thin layer goes on top of this cold platform. And because the silicon thickness is 2 millimeter, it immediately starts stacking the heat of the material. And when you fill it with water, the water started to turn into ice in 4 seconds. So on the screen, on the photo on the left-hand side, right-hand side, you can see the ice formation in the channel. So this was great because then the whole line, we were able to fulfill, we were able to fill the whole liner or the whole liner surface within 5 minutes 15 seconds, which is great because otherwise it took me 75 minutes, and that was overshoot for the first layer to be to cure. Basically it was over curing because it takes so much time to fill these things, and it wasn't bonding to the next one. Then on the graph we have done a preliminary endurance test for the liner, and without any separation issue between top and bottom layer, it reached a 35 Newton. It reached a 35 psi. So this is more than required. We are operating around 20 psi. So it was structurally integrated. Then the last part was actually looking into a manifold design, because as I was just now talking about, like this needs to be a very small box. This manifold, the first control circuit, you can see from the size of the computer there, it was like 35 by 35 centimeter. And then by using the same water freezing principle, top and bottom layer, I created that silicon block there, which I call it Flexifold. The top holes are for the valves connected. The bottom holes are for the pressure sensors. So on the next photo, there is the bottom view where the electronic circuit is integrated into the Flexifold. So inside of the Flexifold, there is a complex air channel pattern. And basically the command you send from your phone is reconfiguring the air channels inside of the Flexifold. It is a manifold, but it is a flexible manifold without requiring any CNC machine or anything. You can actually do it with a 3D printer just for the mold and silicon. So it's a very low cost solution to this. And that enabled us to create a control design, a control box, which is smaller. It is actually the size of a smoke cigarette package. And thanks to these the pump, getting rid of the pump because we use the compressed air, and the flexifold, it got into a very concise system. The next stage, what we are trying to do is integrating the canister into this box. So we recently got 500,000, so £500,000 grant from Innovate UK for my startup and for Imperial College to look into this integration. How we can make it even smaller, including the canister. As a result, where we are now is like plan for completion is doing still characterization of the freeze filling method, and also running a quality of life questionnaire with amputees, but also now writing ethics application for the effect of the liner during gait analysis in a motion lab, basically. Before ending it, I would like to share one little thing. This is just for public awareness. As I said in the beginning of the presentation, amputees live dependent on hospitals because of the fitting problems for the rest of their lives. And prosthetic liners are crucial for comfort, and that's why almost all amputees are wearing prosthetic liners. And a robotic liner, either this one or another one, any other research, we are, or Imperial College is proud that this is the first of its kind research in this field, is a robotic liner that will enable amputees to adjust their fitting without going to clinic. So I have a startup based on this. We have so far raised £1.2 million for grant funding. We've been selected by European Union as one of the most successful 15 startups for societal impact as well. And it's a multinational project. So we are 19 people across Europe, including the UK team. I have trained 9 master students on this project as part of my PhD. Go to conferences and congress just to increase the public awareness. We have won so many awards as a project on this on this innovation. Investment awards, academic awards, public like societal awards. We want to get to market next year after I finish my PhD. There are still CE mark medical device regulations and clinical trials pending, but that's basically what we are aiming for. But so far so good. Thank you very much for your attention and for listening. I am very excited about the questions you will ask, hopefully.
Thank you very much for your presentation. I have a question for you. What would happen if something went wrong with the high pressurized valve? Isn't that dangerous carrying that pressure on our legs?
Yeah, great question. This was a question that I also asked myself like 2 years ago. So it is something that you actually use often in your life without knowing it. When you go into any aircraft, so I'm going to give this aircraft example because in aircraft you have even a low pressure environment outside of the aircraft. Even in the aircraft, the life jackets, the yellow ones they show you, has these canisters inside. So when you pull that string to inflate it, you basically pierce the canister to release the gas to inflate it. So these devices, although they're so high pressure, the way they are manufactured is pretty standardized to the level that they are used in angiography devices like cardiovascular surgeries, carbon dioxide canisters. They are used in aviation industry, which is one of the most vulnerable situations, like being on a plane thousands of meters above the ground. But yet they have this for every passenger. It doesn't cause any, it doesn't impose any risk in that sense. So in terms of carrying it on the leg, because the way they are manufactured are regulated as a medical device, their safety standards are, their safety factors are way above 900. So if it has 900 psi inside, the actual canister is manufactured for 3 times more of this pressure to bear it. So that's called the safety factor. And because it's a regulated, if you're going to use in medical devices, it's a regulated industry. You cannot just use random ones. You have to use the ones that are safe to use.
Okay, thank you. One more question. Do you have any research to tailor with nanotechnology science to your studies?
No, not at the moment, because this research by itself, like I tried to summarize in 50 minutes, had so many problems related to materials science to find it the right balance. Nanoparticles, nanomaterials would be on the horizon, but we don't anticipate anything at this stage before we see the reaction of amputees on the liner.
Okay, thank you. That was all. Thank you for your answers and your presentation today.
My pleasure. My pleasure.
Well, welcome back. Now our next speaker, who's a good friend of mine, Erdem Sezgin. I've known him for over 13 years now. We were both students in Yeditepe University. He was an undergrad and I was a master's student then, and we worked in the same project for some time. And then he graduated and he went to Dresden, Germany, Max Planck Institute, where he finished his PhD in 3 years. He's such a genius, by the way. I have to admit that. And after he's done with his PhD, he continued for his postdoctoral studies in Oxford University in London, England. And then he stayed there for another 3 years in a very well-known laboratory. And after that, he went to Sweden and he built his own lab. He's a biophysicist. He's a nanotechnology guy. He's got everything in him, and he's got his one of his books actually published. It's a Turkish book. He will probably tell us about it today, and his other studies he's doing right now. Erdich, yes, it's your turn.
Thanks so much, Esra. Thanks so much for the invitation. It's a pleasure to be here. And I must admit, all this scientific journey, it was no time period more fun than the period that we did together in Yeditepe that summer. So it was a lot of fun. So today I will talk a bit about what we are doing in the lab, what we have been doing to understand the cells in a detailed manner so that we couldn't understand before because of some limitations. So as you can understand from the title, I will talk a bit about light and a bit about synthetic biology. But first, I'd like to give you an introduction of a cell again. So this is basically a picture of a cell that you would see in a textbook. You would see these compartments inside, very specialized compartments. They have specific jobs. And one structure that is particularly interesting for us is the plasma membrane. So plasma membrane is the structure or organelle, if you like, that is separating inside and outside of the cell. And this means this is quite a selective structure that would allow certain molecules to pass through, certain molecules not to go through. And that is why you can think of as a barrier between outside and inside of the cell. And it's not only for material going through, it's also signals to go through. Imagine insulin, right? Insulin needs to act via some receptors, and the insulin receptor sits on the membrane. And you have hundreds of different receptors sitting on the plasma membrane, and that is why it's also a hub for signaling. That's why it's quite an important, if not the most important organelle in the cell. But if you think about the cell membrane in the textbooks, I'm sure you all remember from biology courses or cell biology courses that it is drawn like two parallel sheets of lipids, phospholipids, and some proteins embedded in it. And it is not really an accurate picture of the plasma membrane. Last 2 decades, there were a lot of research going into the structure of the plasma membrane. How can such a simple phospholipid and protein structure fulfill so many different functions and in such a regulated manner? And that is why this research figured out that cell membrane is more heterogeneous than we think. There are a lot of phospholipids, this lipid structure I'm sure you're familiar with. These lipids, some lipids have affinity for each other. Some proteins have more interest for certain lipids. That's why they bring together their own microcosmos and it becomes a very heterogeneous structure. And just remember this, if you think about a single mammalian plasma membrane, a single cell has hundreds different types of lipid types, right? So this makes really heterogeneous structure, and this makes a very, very big complexity when you think about the plasma membrane. And this heterogeneity happened to be functional. It's not only passive consequence of this compositional complexity. So we know that if plasma membrane was not heterogeneous, signaling would be either all the time active or all the time passive. So this heterogeneity is somehow regulating if certain signaling events are active or passive. So besides this heterogeneity we are talking about, there's also something that biophysicists are particularly interested in, the collective properties. I'm sure you watch this interesting movies of birds, that a flock of bird, how they behave. It's not one single bird or one single ant how they behave, but it's the collective behavior of the population how they behave. And this is exactly what is happening in the cells as well. We have certain lipids, lipid types, but overall, when they come together, they bring a collective behavior, such as stiffness. You heard from the previous talk, there are a lot of physical properties that are important for cellular life. The stiffness is very important. Imagine your immune cells flowing in the blood, and they sense somehow, somewhere infection, and they have to pass through this epithelial layer to go to the infection site. How would they do this? They need to be stiff. They should change their stiffness so that they go through this very tight junctions of the cells. The curvature of the cell is very important. For molecules to go inside the cell, they should be endocytosed. The curvature is very important. The membrane tension is very important. The rigidity, deformability, these things are super important for cellular life, but we usually ignore them as molecular biologists or cell biologists. But biophysics is exactly filling this gap. Instead of only focusing on the identity of the molecules, we start focusing on collective behavior as well as the physical properties of this. And importantly, these collective properties such as rigidity, viscosity, stiffness of the cell changes in diseases. That is very important. I'm going to show you how they change in a bit in the disease models that we are interested. So why are we interested in collective biophysical properties? If there are already so many advanced omics approaches, right? We have transcriptomics, genomics, proteomics, lipidomics. You can get all single molecule sensitivity of a cell. Why are we doing biophysics? Biophysics, as I said, it's a collective behavior. It's beyond all of this. It's a collective behavior of all these compositional elements. And eventually you get something out of this that you cannot get by looking at single components. So for us, what we are doing, we are basically trying to map cell and cellular states in a biophysical aspect, like stiffness, the forces that cells apply to other cells, or electrical aspects or potential aspects of the cells. And eventually we want to do mapping of the biophysical properties of the cells so that we can understand how diseases are affected in terms of biophysics, how we can manipulate the biophysics of the cells so that we can go back to normal, healthy phenotype. So I just want to give one example of this very interesting collective behavior that is also partly the consequence of the heterogeneity we're talking about. So I'm sure you all know about saturated fats, unsaturated fats, right? We usually talk about this in terms of health, but also in terms of plasma membrane structure. This is also such a critical thing to know. So remember, saturated lipids, we have, when we don't have double bonds in the acyl chain that I'll show later, these are saturated. If there are double bonds in the lipid structure, then we have unsaturated lipids. And if you mix saturated lipid, unsaturated lipid, and drop a bit of cholesterol in this mixture, what you get is this amazing phase separation. So saturated lipids goes to one phase, unsaturated lipid go to other phase. Cholesterol, like saturated lipids, it goes with the saturated lipids. That's why it forms this liquid-liquid phase separation. So both entities are liquid, but they're still separating from each other. Imagine like an oil-water, but here it's both lipid structures, but the structures are different. And now this liquid-liquid phase separation becomes a center of cell biology these days, because this has been observed in membranes more than 30 years ago, but now in cytoplasm, in nucleus, people started observing this liquid-liquid phase separation. And transcription, for instance, apparently is very much regulated by this liquid-liquid phase separation in the nucleus. So you can see domains that split, domains can merge. So this is exactly the property of a liquid-liquid phase separation system, that the domains should be actively either splitting or merging together. So this is just an example for you to understand how collective behavior actually comes from heterogeneity and can contribute to the cellular function. So in the lab, what we try to understand is, first, we want to understand how the plasma membrane is structured and what is the biophysical properties of plasma membrane in health and disease. can we somehow manipulate this biophysical properties in disease states so that we go to healthy phenotype, so that we can contribute to treatment of the diseases. And these diseases, we are not focusing on single diseases, mostly whatever could originate from the plasma membrane, we are actually interested in. And these are mostly metabolic diseases, diabetes, obesity, cardiovascular diseases, aging, they're all related to the plasma membrane. But of course, having such a central role, why couldn't we solve it before? I mean, it's no brainer, right? Plasma membrane is so important as a hub. Let's focus on it and solve it. Why don't we do it? There are a couple of caveats. And so the first caveat is, of course, if you want to understand the plasma membrane properties, you need to have proper probes and techniques to understand the plasma membrane properties. And we don't have those techniques yet. We have it now, but that's why we are always in the techniques development field as well. So second, there is a resolution barrier. If you think about this plasma membrane structure, this small heterogeneity that you see, different colors that you see, they're in nano scale, which means they're 5 nanometer, 10 nanometer scale. But if you look at a cell with a conventional microscopy technique, light microscopy, its resolution is 250 nanometer, which means you look at 250 nanometer, and whatever color you have in this 250 nanometer, it's not going to show as different colors, but it will be only one color, because this is your resolution. You can resolve only one value for this signal, right? For this observation spot. And that is a big problem because you cannot resolve this nanoscale details. And another problem is the complexity. So as I mentioned before, we have hundreds of different types of lipids in a single mammalian cell. Plus, we have all the proteins. Plus, we have actin cytoskeleton that is giving strength to the plasma membrane. Plus, there's sugar layers, glycocalyx on top of the plasma membrane, and we keep ignoring those structures, and it makes plasma membrane very complex. If you want to understand what is going on in the plasma membrane, what is the role of one single component of the plasma membrane to cellular functions, it is very, very challenging due to this complexity. So we have to take care of all these things first to understand the plasma membrane completely. And that's why in the lab, we focus on different areas to understand, to visualize plasma membrane biophysical properties. We are developing chemical biology tools to understand small details that is not limited to our conventional microscopy limit. We are developing super resolution imaging. And of course, to analyze this kind of data from single resolution, super resolution or single molecule techniques. These are new technologies, so we have to do software development as well. And to overcome the complexity problem, we are doing synthetic biology. So that's what I'm going to talk about today a bit, synthetic biology as well as how we are using light. And of course, we always do omics approaches as well, classical omics approaches to give fingerprint to the biophysics. So that's also very important. So I'm not going to mention all of them today. I will mention briefly chemical biology, what we're doing, because that will be interesting for some people who want to be in the interface of chemistry and biology, and super resolution imaging who want to be in the interface of physics and biology, and synthetic biology who want to be in the interface of engineering and biology. So first, chemical biology. But again, let's remember the structure of the plasma membrane, the phospholipids and the proteins. And phospholipids, as I promised, I'm telling you how the saturated lipids look like. Saturated lipids, they don't have this double carbon bonds. That is why saturated lipids are really well packed. And this packing makes a difference. Imagine butter. Butter is saturated fatty acids. That's why they pack well. That's why they're solid. But unsaturated lipids, they have this double carbon bonds. That's why they can't pack well. This is physically not possible. This kink doesn't allow them to pack well. And that's why they're liquid, like unsaturated olive oil, right? In the plasma membrane, it's also the same. So if you have a phospholipid, this yellow part is the fatty acid part, and the blue part is the head group. And if you have a acyl chain that is saturated, these phospholipids can pack really well, really tightly, but unsaturated lipids cannot pack well. So this is basically telling us how rigid is the membrane. can we come up with an index that would tell us what is the rigidity of membrane in different states, in different diseases, if the rigidity is somehow changing in diseases? It makes sense, because if you think about some diseases like aging, we think the body becomes rigid, but actually in the cellular level, we postulate that also the cells might become rigid, but we'll come to that later. But first, we have to come up with an index. We have to come up with some probes, imaging technologies, so that eventually we come up with an index that tells us how rigid the membrane is. And for this, we apply some of the smart probes. If you are familiar with fluorescence, you would remember that we excite these fluorescent molecules with a single wavelength, and then they emit light at different wavelengths. But this wavelength emission spectrum is usually fixed. It doesn't matter if you go to water, if you go to ethanol, if you go any other solution or pH, it usually doesn't change for fluorophores, for fluorescent molecules. But for smart probes, it's a bit different. So it changes its emission. For instance, this dye, Lodon, it changes its emission depending on the polarity. That's why we call it a smart probe. It's not only a dumb probe that goes and then gives you light, but it's a smart probe. It gives you light depending on the environment. So it informs you about the environment. So if you put in a very polar environment, such as ethanol, you have very red-shifted emission. And if you put in a very non-polar environment, such as chloroform, you get very blue-shifted emission. Well, great, chloroform, DMSO, ethanol, great solvents, but how is it going to help us in membrane research? Again, if you remember that saturated lipids are packing really well, they don't have a lot of space for any other thing to be in the membrane. These black dots are water molecules. But unsaturated lipids, since they have a lot of space, they have a lot of water molecules running around in the membrane. So water is polar. And if some membrane involves more water, it becomes more polar. So that's why if you have a membrane composed of unsaturated lipids, the maximum emission of this dye is more red-shifted compared to saturated lipids. So this dye, for instance, Lodon, has 440 nanometer in the ordered phase and 490 nanometer in the disordered phase. When I say ordered phase, it's basically saturated, it's ordered, packed. Disordered phase is unsaturated lipids, not packed well. That's why it's disordered. It's not so ordered. So, of course, how are we going to image this? We need to also develop some imaging technologies, and that's why we have this spectral imaging modality. So how we do this? We get the emission from your sample. Of course, you excite with a laser. You get the emission, and then disperse your emission with a prism. And then this emission falls into a multi-channel detector, so that every single channel of this detector is a single wavelength. And then you can put all the single wavelengths together to reconstruct a spectrum for each pixel of an image. And then using this wavelength shift, right? In one membrane it's 440, in the other membrane is 490. If you just get the ratio of these two wavelengths, the intensity ratio in these two wavelengths, you can get an index. Don't worry about the details, just remember this. This index, generalized polarization index, is an index of membrane rigidity. It changes between +1 and -1. +1 means too rigid, -1 means too fluid. And everything in between is basically telling how rigid the membrane is. And color is not random. Color code is basically, as you can see here, this is the color code. If you see reddish, it becomes more ordered, more rigid, and greenish, bluish is less rigid. And of course, it has all its quantitative values, right? All right, so this Lodon probe was great. It was developed in the 90s. We used it for a very long time, but we were never happy with it. It's not really great dye. It's really dim. It's not bright. It goes inside the cell as well. So it labels the plasma membrane, which is this outer layer, the bright layer, but it also goes inside. As you can see, it's a lot of membranes inside, right? ER has membrane, mitochondria has membrane, Golgi has membrane, lysosome has membrane. It labels everything. It gives information on everything. But what we want is a probe that gives information on the plasma membrane only. That's why we developed last year this new probe. We call it Pro12A, which doesn't go anywhere else. than plasma membrane. So now with this probe, we can actually see only the plasma membrane so that we can do more high throughput measurements that doesn't affected by internal membranes like other probes. So what do we use these probes for? So now I'm not going to go into detail on the biological applications, just want to give you snapshots what we are doing. So we have a lot of different projects on a lot of different biological questions. But just to give you an idea what could be done with this probe. So aging, I gave already this example. With aging, we know that body gets more rigid. You cannot be more flexible anymore. But in cellular level, this is also true. So we know that actually in the old cells, if we get cells from old mice versus young mice, we have more rigidity in the old mice. So in aging, it's very important to be able to understand this membrane biophysical properties. Another disease model is lysosomal storage disorders. In these diseases like Niemann-Pick C, Gaucher disease, Tay-Sachs disease, in these diseases, the cells cannot traffic most of the lipids properly to the plasma membrane, but instead, most of the lipids are trapped inside the lysosomes or late endosomes, such as cholesterol. Cholesterol is such an important molecule. It's 40% of the plasma membrane is cholesterol. So if you look at the plasma membrane, almost every third lipid is a cholesterol. But if cholesterol is trapped inside internal structures and not trafficked properly to the plasma membrane, what you see is, for instance, here in the Niemann-Pick C, you see more bluish compared to wild type, which means in the Niemann-Pick C, the cells are more fluid compared to wild type, which is rigid. So it has cells should get an optimal rigidity. It shouldn't be too rigid, it shouldn't be too fluid, and different diseases affect it in different ways. And other things, of course, signaling events. So we try to understand how plasma membrane is affecting signaling. And second, how signaling is affected by the plasma membrane. And both of them could be studied by using this probe. So here, for instance, we investigated the wind, how wind signaling affecting the plasma membrane itself. All right, so far what I showed you was all limited to conventional microscopy. The spectral imaging is still conventional microscopy. It has a resolution limit. So just to briefly tell you why our microscopy techniques have resolution limits. It's a physical law. It's like gravity. It's called diffraction. If something behaves like a wave, which light is, right? If it hits with some fringes of a matter, it creates waves. Imagine like water, you drop a small stone, and when water passes through a small slit, it creates this wave, right? And this is exactly what's happening in a microscope. And this wave has a property. If the wave length has certain size in the light, let's say we're using visible light, which has 5 nanometer wavelength, the resolution that you can get with this light is limited to half of the wavelength. So if you remember this fact, you're already a better microscopist than most of the scientists. So resolution of a microscope is limited by roughly half of the wavelength that you're using. And this is a fact. This is a law. We cannot break this, but we can circumvent this. Because we need to circumvent this. We want to understand what is below 250 nanometers. We want to understand the structure of virus, which is 100 nanometers. We want to understand the structure of mitochondrial cristae, which is smaller than 250 nanometers, right? And that's why you have to circumvent this. This is how curiosity-driven science finally pays off. And that's why people develop super resolution imaging in the last 2 decades again, and they got super resolution microscopy got the Nobel Prize in 2014 in chemistry. And one of these super resolution technologies is called stimulated emission depletion microscopy, STED. Again, no details, but just briefly speaking, when you excite your sample, doesn't matter how small your sample is, it could be infinitesimally small, 0.0001 nanometer. It doesn't exist such a particle, but imagine that it is such a small particle, but still the signal that you are going to get is limited to half of the wavelength. You excite this small thing, it brings you 250 nanometer signal. This is the signal that comes from your sample, And what you do smartly, you hit your emission with a donut-shaped depletion laser. And this laser has the ability to kill the emission. So what you have then, you get the emission, you kill in the donut shape, which means you kill all the peripheral signal, but the center, because it's a donut shape, the center is not affected by this killing process. And that is why you only have eventually only in the central spot that is untouched by this depletion beam. And instead of 250 nanometers, you have 20 nanometers, which means you increase the resolution 10 times. You could go smaller scale, 10 times smaller scales that you could do with conventional microscopy. What can you do? Since the inception of this super resolution ideas, there are hundreds, thousands different papers using super resolution microscopies, solving structures in the cells that we couldn't solve before. And you can do also in live cells, right? So now you can say, well, cryo-EM can do everything now. Why are you doing this? We are doing this because we can do in live cells. We can investigate without the artifacts of many other technologies. This is the main strength of the super resolution imaging. This is, for instance, a confocal microscopy. Confocal microscopy, by the way, is still the mainstream microscopy. We also, 70–80% of the cases, we still use confocal microscopy because we don't need such high resolution for most of our stuff. But if you need super resolution microscopy, then you have to use, if you are after nanoscale details, such as this structure, which is nuclear pore complex, in confocal microscopy, you can't see anything. But now if you go to STED, you can see this nice subunits of one protein, and in the middle, there's this another protein. This is solving basically for you the nuclear pore complex with light itself. So what do? We apply, of course, this super resolution microscopy in combination with our smart probes. And what do we see now? We see very small details that we can't see with confocal microscopy. You see there's like bluish versus greenish. This very small blue dot is a small island that enriches some of the proteins so that these proteins are active only in this zone. And we don't only see this, we can now actually, with the smart probes, because these probes are smart probes, we can also quantify the biophysical properties, the rigidity of this domain. So we know that this is less rigid than the rest of the membrane. And how much less rigid, right? We can also quantify this. You can also see other things that you couldn't see before, like endocytosis. Like endocytosis is key for cells. It has the material uptake from the outside to the inside. But we couldn't resolve this because these endocytic vesicles are very close to the plasma membrane. But now if you apply super resolution, you see the vesicles clearly, you see the plasma membrane clearly, and you can quantify what is the rigidity of these vesicles versus the plasma membrane. Well, so far what I showed you was all 2D enhancement of the resolution. You look from the top and you try to enhance the resolution in 2D. Just briefly speaking, you can apply this donut shape in a different pattern so that you don't only kill the signal in 2D, but also 3D. So instead of having, for instance, a profile picture of a cell that you cannot distinguish anything, imagine this is just a side view of a cell. Now we look at the cells in the 3D, and you can see all the details now. This is the top membrane, bottom membrane, internal membranes. You can see all the details now by applying the 3D. And this of course helps us a lot because now we can see all these processes like budding, endocytosis, exocytosis in a very detailed manner. So I hope in this first part, I could convince you that smart probes are really smart, and combination of them with super resolution microscopy definitely gives us all the nanoscale biophysical properties that are important for the cellular physiology. So in the second part, I'm not going to go into detail, but in the single molecule approaches, what we are after is the dynamics. So if you think about it, all the pictures that I showed you previously, they're all very static. It's just one single snapshot. But if you think about the plasma membrane or the cells itself, the cells move all the time, right? So cells are not they're not static structures. Inside the cell, the cytoskeleton actin moves all the time. Organelles, lysosomes, mitochondria, lipids on the membrane, everything moves. Diffusion is life. If you cut the diffusion, the cells are dead. That is why it's also important to get this dynamic aspect of the plasma membrane and cells in general. So for this, we are using a lot of other technologies, but one of them is fluorescence correlation spectroscopy. So here we get the diffusion of the molecule by looking at one single observation spot, molecules moving in and out. And from this moving in and out, we get a correlation function that tells us how long a single molecule takes to go through this focal volume. Since we know the size, we can also get the diffusion of them. And this is also important. Why? Because now we can actually measure the mobility of things inside the cells. So here's how we measure the mobility of molecules, lipids, and proteins in the cells, in live organism like zebrafish. Or it's not limited to membrane, of course. We measure how molecules are organized in the nucleus. And we figured out that some molecules are more clustered than others in the nucleus. And also, it's not limited to eukaryotic cells. We can also look at the prokaryotic cells like bacteria, right? So here we figured out, for instance, some of the complexes in bacterial membrane are already formed in the cytoplasmic space of the membrane. So they are not forming in the membrane, but they're forming the complex in the cytoplasmic site and going as a complex to the membrane of the bacteria. So, of course, what we combine is also to get the nanoscale diffusion, we combine this STED approach, the super resolution approach, with the FCS approach, this fluorescence correlation spectroscopy diffusion approach, so that we can get nanoscale information as well. But I'm not going to go in detail. In this part, I just wanted to show you that the diffusion is super important. We shouldn't really ignore diffusion as a player in the cells. We always consider diffusion as a very physical phenomena that doesn't have any effect on biology, but this is wrong, because if you think about the receptors in the plasma membrane, their diffusivity determines how fast they will find their ligands. And that's why diffusion is very important. FCS and STED FCS are really good ways to understand this. So in the last bit, I will just shortly show you how we use synthetic biology to mimic some of the properties, some of the processes in the cells, and try to understand the biophysical principles. So for this, I need to remind you again, plasma membrane is very complex. Lipids, a lot of different lipid types, proteins, sugars on top. And especially for lipids, proteins, let's say if you want to get rid of one protein, what would you do? You just go CRISPR-Cas, knock out, and then protein is not there anymore. But for lipids and sugars, it's not that easy, because there are pathways, there are common pathways for lipids and sugars. So if you cut one single enzyme, it doesn't affect only one lipid, it affects whole class of lipids. So you basically get rid of a lot of different types at once. So it's not as easy to genome engineer for lipids and sugars. That's why we follow a different path. Instead of this top-down, knocking down approach, we are going bottom-up reconstitution, which means we start from scratch. We start making lipids, membranes, and then add proteins on top, sugars on top, extracellular matrix, cytoskeleton, so that we can have a minimal cell. And then we investigate multiple different biological questions, trying to understand what is the role of each element that we can reconstitute in. So the beauty of this approach is you control the complexity very, very tightly. You decide what lipids will be in your system, what proteins will be in your system, which part of glycocalyx will be in your system. So this tight control makes you are able to basically understand the role of each molecule. So for instance, how are we making lipids, only lipid structures? We just buy lipids, right? And then deposit these lipids on an electrode. And then we apply electric field. In an aqueous solution, these lipids, they form these vesicles. I don't know if you're seeing these vesicles. Of course, this is really hard to capture in a camera. That's why it's such a crappy movie. But I think it overall shows you the point that you have actually some vesicles forming. And then you isolate these vesicles. You can fluorescently label them. You can look at them in bright field. The beauty of these vesicles, again, is the lipid composition of these vesicles are exactly what you put in your wire, in your electrode. So if you want 30% saturated lipids, 50% unsaturated lipids, 20% cholesterol, that's all up to you. Whatever you put, you will get. So these are only lipids. Of course, one lipid membrane is not going to be a mimic of a cell, But now we can also gradually put proteins on top. What do we do to put the proteins on top? In the lipid mixture, we also put some nickel NTA lipids, which means in the head group, there's nickel NTA group. This nickel NTA group recognizes his tag proteins. So if you put his tag proteins, which are mostly available, then these his tag proteins are recognized by the nickel. So then it binds and your protein is presented on the surface. So now what you have is a vesicle, which has a lipid composition of your like, and then protein composition on the surface of your protein of interest. Whatever proteins you want to put, you can put on the surface. If, for instance, you put the histag protein, this protein is recognized by a T cell, this is what you get. So T cell recognizes your synthetic cell. And of course, this contact is not such a static contact, it's very dynamic. You put the protein on top, this T cell tries to do whatever it needs to do, whatever this protein contact tells the T cells to do to the synthetic cell, right? So here, this contact is quite a clean contact now. We can understand how immune cells forming this contact, how they recognize, first of all, the synthetic cells, how they try to kill, and what do they do? What are the biophysical principles of this? So I think these are quite important aspects of the immune signaling, right? So in T cells, especially in the body, when, let's say, you reach a certain age, the tumorigenesis in the body is actually a normal process because you accumulate a lot of mutations. But then immune cells navigate through the body, they recognize the bad malfunctioning cells, they kill them. So you might get tumor cells in the body, but T cells actually, the immunity, let's say, taking care of them. But how do they take care of them? We have so many cells. How can they screen all the cells possibly, right? So the screening process is important. And they should recognize one malfunctioning cell as a malfunctioning cell. So this recognition is important. And then they form this contact, which we call immune synapse. This contact formation is important. And then they kill via the synapse. It is also important. And all these things, all these processes happen with biophysical principles that we cannot understand in a complex system. That's why if you can reconstitute the certain elements that you want to study the role of, that's exactly what you're going to do. You're going to understand which molecules are important for what processes and what are the biophysical aspects of immune cell signaling. So we study two different signaling events. One is T cell signaling. T cell is basically major adaptive immunity cells. Imagine you have innate immunity and then you have adaptive immunity. If everything else fails, T cell is your last defense. So that's why it's very important to have the T cell receptor signaling understood. This is probably the most commonly studied immune signaling as well. And another rather problematic signaling is Fc epsilon receptor signaling. This is the allergy pathway. If you have allergy, these are the people that you need to blame. But they are very similar. These two signaling pathways are quite similar. I'm not going to go into detail. I'm just putting this complicated picture to convince you my synthetic biology approach, because it's too complex. It's very difficult to understand everything. That's why we just put everything to synthetic systems with the complexity that we want. But mainly, there is one single thing that initiates both signaling. This receptor, either T cell receptor or Fc epsilon receptor, should be phosphorylated. That's it. That is the only thing that you should remember. If the receptor is phosphorylated, signaling becomes active. What phosphorylates the receptor? A couple of molecules inside the cells, like LZK in the T cell, SYK, for instance, LIN in the allergy pathway, which is usually basophils and mast cells in the body. But then if they phosphorylate all the time, this is not going to happen, right? So if they phosphorylate the receptors all the time, this is not going to work because our cells will be overly active. We don't want our cells overly active because that's called autoimmune disease. So we have actually an interesting aspect that some proteins are phosphorylating and some other proteins dephosphorylate. So how come these phosphorylating proteins somehow winning the war between this balanced war when there's a threat in the body? So here I show you some of this. So here you can see this is our synthetic cell. And we put T cells on top. T cells, you don't see the T cells, but you see the contact zones by purple. This magenta line is the contact zones. And you can see in the contact zone, probably in this picture, you will see a bit better. So this is our synthetic cell in the middle. This is a mast cell that starts the allergy pathway. And this is our activating, this phosphorylating molecule. This is our receptor. So receptor is next to our phosphorylating molecule. And this protein is dephosphorylating molecule. So this would be the one that would balance the activity of this one. So CD45, it was a battle between CD45 and SIC, but now this phosphorylating molecule wins the war because CD45 is completely excluded from the contact zone. And now we start to understand, of course, this contact region is an immune active region because there is nothing to stop the immune activity anymore. But how come the CD45 is completely excluded? And here comes biophysics. So in molecular biology, cell biology, biology approach, you would identify what is important, which molecules are important. But in biophysics, you try to understand why they're important, what are the properties of these molecules that would play a role. And here, CD45, this is the real structure of, cartoon of real structure of CD45. You can see it's a very tall protein here. LCK, it's intracellular, it's not affected by the extracellular space at all. If the contact between this immune cell and our synthetic cell is very tight, this CD45 molecule, the tall molecule, may not fit in. And that is why CD45 might be excluded. Of course, we test this by making a short CD45, and short CD45 is not excluded at all. And that is why this short CD5, when we transfect the cells with short CD45, these cells, they don't get activated anymore because on the immune active zone, there is molecules still stopping the signaling. So signaling is stopped. So that is why this simple biophysical principle, which is the size of a protein, is such an important aspect of immune signaling, both in T cell signaling and in Fc epsilon receptor signaling, which is the allergy pathway. We also try to understand in the natural killer cells, B cells, they're all important. The size of the molecules are very important for all of this signaling. And this is simple biophysics. So I hope in this part, I would show you the synthetic biology tools that we develop are important to isolate the system that you want, put the complexity of your will, and then study the roles of the components that you put in the system. And you can do in 2D, 3D systems, like I showed you here, the 3D systems. And by using these systems, you can actually get the physical principles, all these biophysical principles that could be actually ruling the cellular life that we couldn't solve by only looking at the identity of the molecules. So with this, I'd like to finish. If you are curious about more of our research, please visit our website. And of course, there are many people I need to acknowledge. I'm not going to go name by name. We have a lot of collaborators that contribute to this work one way or the other. This is my lab. And again, I'd like to thank you for your attention and Esra for invitation again.
Well, I thank you personally, first of all, for this fascinating talk. It was very inspiring to see all of the work that you have mentioned. Just for today, of course, you have more than that. I know that, but you only talked about a small portion of it. I know that. Well, as a cancer biologist, I have a personal question. Now, as you know, as the whole world knows, actually, cancer is a very heterogeneous population. So I was wondering if you ever had a chance, I know you mentioned a little bit about the diseases that you had worked at the beginning of your talk, but didn't talk about really much about the cancer. But I was wondering if you ever had a chance to profile if there is a change in the plasma membrane constitution in terms of diffusion as the cancer cells become, not when they're not from your malignant, from benign to malignant, or if there's through the evolution as they're evolving towards the malignant properties. Do you think you ever see them under the microscope? You ever had a chance?
Yeah, super good question, and this is exactly what we are doing, Esra. So we actually just submitted one grant with BioMedTech. We collaborate now in this project as well, try to understand So it makes sense, first of all, thinking about this malignancy versus biophysics, right? So if cancers start becoming metastatic, they become dangerous, right? Metastasis is the main problem in cancer. And metastasis means cells should move, their migration potentials should increase. And the migration potential is very much related to biophysics, the elasticity of the cell, right? So we don't know yet. There are a couple of studies, of course, they're showing with the atomic force microscopy to see if the stiffness of the cell changes. And there are a lot of preliminary results that it changes, but we need to do high throughput, as you said. So to understand this biophysical aspects in medical world, one cell at a time in the microscope won't work. What I showed won't work to understand in the medical aspect, right? We have to do high throughput. And that's why we're developing at the moment to measure millions of cells from multiple patients instead of just measuring the cell lines, right? Then we will understand the real heterogeneity in biophysics, map the biophysical properties, and correlate it with the disease phenotype.
Cool. Am I included?
Can
Always.
I ask a question?
Yes, Halil Hocam, please.
Okay. I enjoyed your talk very much. It was very impressive.
Thanks so much.
Very impressive. And I start to see some applications, and possibly you have seen them before. In terms of biosensors, you can build many biosensors based on your principles. Maybe one including sensing of COVID with this virus. Did you do anything about it?
Yeah. We have a couple of grants that we are looking at, not only COVID. So we got the grants for COVID, of course, but we try to understand this biosensors in terms of, first of all, how virus binds. We are interested in the membrane, right? We try to understand how virus binds. I mean, when we think about the membrane, we always ignore the super thick sugar layer, right? So there is a glycocalyx extracellular matrix and the receptors at the bottom. How would virus find it and how they bind it, right? And then the synthetic systems could be, as you said, it could be a sensor. We have some grant applications. We want to design as vaccines as well, because you can make a small particle with any protein on top, right? You can deliver as a vaccine. I mean, we have multiple. Last year forced us to think about virology more, as you can appreciate, right? So we diverted a lot of our topics to more or less host pathogen interactions that we were interested. We were interested more in HIV, but now we are more interested in every other microorganisms, including antibiotic resistance bacteria, immune reactions to them, and how we can use our synthetic systems as tools, like sensory tools for infections as well.
Cool. So we will see you
very
in the COVID
interesting
field as well.
Thanks so much.
There's one question from YouTube. I wonder, may neurotransmitter like glutamate, vesicles and presynaptic neurons be examined with super resolution microscopy in case of excessive electrical activity?
Of course it can. I think it's how it started. One of the first samples are actually the synaptic vesicles, right? Because they are around 70 to 120 nanometers, right? And if you look at even sometimes smaller, you look at with the normal confocal microscopy, you don't see anything. You just see a big blob of signal, right? And then they apply super resolution. They're really very, very good. And the first simulation came from the synaptic vesicles. So they simulated what would it look like if your resolution was 10 nanometers, and then you could see super clear vesicles, right? So yes, it has been done, it is being done, it will be done.
Cool, thanks. Well, I have one last question about your book. Can you tell us about your new book, your published book?
Sorry, yes, I didn't want to do some shameless self-promotion here, but since you asked, yeah, we are with colleagues from all around the world, all these academicians from Turkey, they went to really good universities all over the world, MIT, Harvard, Oxford, Cambridge. So we decided, why not writing a popular science book in Turkish? because popular science books exist a lot in English, in other European languages, but we don't have much of these books written by the experts of their field, right? So now we have 17 scientists. They compiled good summaries that everyone can understand about their own work. And now it's called Genetikten Kuantuma, Genç Bilimcilerimiz Anlatıyor. So now it's you can get it from most of the bookshops or online shops. So
I'm
sure
curious. I would like to read it as soon as I can.
I'm sure you will enjoy, because I read it a couple of times because I edited the book, and every time I read it, it's like, wow, great! It's something about microbiota, quantum physics. We have how we use technology for peace, as Ur said, right? That he wants to use his technology for peace, and we have a chapter, technology for peace. We have science, philosophy of science chapter, how Kant understood science and how it implemented science, archaeology, genetics manipulations, synthetic biology. I mean, a lot of other things, preservation of ecology. You'll see. I just
Congratulations. I can't wait to read. By the way, there's one more question from YouTube. I'm a med student. I have read in the literature that high cell motility is generally associated with lower cell stiffness. Does cell stiffness always directly indicate low cell motility?
Not necessarily. That is true. There's a general trend, but of course it depends also. Adhesion molecules on the cell surface are quite important as well. So you cannot just look at one thing and immediately say this is causative. There is a nice correlation, but let's say this caterins, adherins, integrins, they're all important as well. So we need to check multiple things, but that is true. We have a correlation.
Cool. I think that's about it. Well, thank you again for your time.
Thanks so much.
For your
So
beautiful
good to see you.
presentation. I would like to see you again in another event. Please do so.
I'd be happy
So
to.
we will go for a lunch break. Thanks again for all of us, for all of you, and we will see you in an hour. Thank you.
Hello again to all participants. Welcome to our this part of Congress. The next speaker will be Associate Professor Yasemin Yüksel Durmaz. She is head of the Biomedical Engineering Department of the Faculty of Engineering and Natural Sciences at Medipol University. Now, we would like to hear your presentation. I hand the word over to you, Mrs. Durmaz. Thank you.
Thank you very much for this kind introduction and invitation. I would like to thank to Dr. Aydemir, who organizes these nice conferences. And so I'm really glad to be with you guys in here. And today I will try to explain a kind of story of our research that some of them are past research, the previously done, and some of them still going on. And also you will see some of the future plans because there's something going on in our laboratory these days. And so let me introduce my talk, which is about acoustically active nanocone clusters for soft tissue ablation. And so when I say soft tissue ablation, actually, I mean something that we call histotripsy. Histotripsy, which is a non-invasive ablation methods that I will run this video, but I'm gonna put them on silence. That's why I'm explaining. It will give you an idea on the visual data. So actually, histotripsy is a kind of non-invasive surgery technique and soft tissue ablation. But in here, the tissue that we would like to ablate, of course, it's the tissue that we don't want, like a cancer. And so normally, clinically used transducer, when they come together in a special design, this concave shape, they have an ability to focus on the certain region and with the spatial wavelength of the sound that can actually create cavitation. This is the process by using the already existing gas pocket in the body, that it can expand this gas pocket, and eventually when this gas pocket bursts, because it becomes energetically really active, when they burst, they actually create excess stress on the So, and during this process, actually, there is no ionization, no pain, because it already tested on the human being, and no thermal temperature increase on the tissue, which is most of the ablation technique actually relies on the temperature increase on the tissue. So how it does, it actually brings this tissue that we would like to remove as an acellular liquid that body over the time can eliminate it. And even the data shows that within short time, you can see in the video right now, it just eliminated. Within a short time, that body puts the new healthy tissue in place of the removed tissue. So it seems like it's kind of nice, non-painful ablation technique. So this histotripsy was discovered in University of Michigan, and they built a startup company, the faculty member that who discovered that they call Histosonic. And so Histosonic actually at the third clinical trial that they're trying to get the approval by FDA for this technique. And they ran a human trial in Spain, and they were ablated 11 tumor on 8 patients, and none of the patients felt the pain during these processes, and they just walk through the hospital end of the, let's say, removal of the tumor or the non-invasive surgery. And after the follow-up, they noticed that, and after 2 months of treatments, almost 80% of the tissue was recovered by the body naturally. So it was successful. Only one patient which had the 3 tumors at the same time in the different locations, and those patients, it just repeated. So, but this was a kind of already metastasized tumor that they realized during this treatment that it already spread out somewhere else. So it seems like histotripsy is a promising and promising and very useful and non-invasive technique, but it's nothing perfect in the science, right? Always there is limitation that you have to take it to the next level. So this is kind of similar. It has a limitations, and that limitation is it requires high pressure. So what I mean with the high pressure, when you run this ultrasound wave at a certain location, let's assume that this light pink region that where we wanted to remove, that here you see that after the removal of that tissue with a sharp boundary, that you can see that cell and the healthy cell just side by side each other, and it doesn't damage the surrounding healthy tissue. But if you or operator hits this ultrasound somewhere here, this region also will get ablated, because here the only selectivity where operator applies the ultrasound where is your focal region. So because of that, it really the operator dependent. You rely on someone else again. Most of the time, it requires an additional imaging technique to really visualize the tumor, to know where we are going to ablate. And so because of that, but this is sometimes not possible, right? For every tumor, you can't image them with the same technique. For some tumor, maybe imaging technique is the best. For other, it's not useful or not that specific. So it's not a kind of selective. If I want to scan the large region with a lot of multifocal tumors, how I'm going to do that? Is it possible to do? If I scan a region, that general region, definitely there are healthy region between the multifocal tumor that I will ablate all of them. So it also had this type of limitation that all of them has similar solution, or a kind of common solution, that if we have lowered this threshold that cause cavitation, expands the bubble and blows up, which is cavitation. If we can lower the required pressure for it, it won't matter even if we scan the large region, only the part that has a kind of agent that can lower threshold will be ablated. So our research actually after this point on focused on addressing this limitation. We can address this limitation. So we thought that if this histotripsy uses already existing gas pocket in our body, which they are normally lower than 10 nanometers, have nitrogen, carbon dioxide, carbon monoxide, all those stuff in your body, right? Just naturally exist. And it uses this gas pocket. So we thought that if we put something in the body that might be initially gas, but it would be so difficult. But we thought that let's make it the liquid at the beginning, but it can transfer into the gas when we introduced into the body. So with a certain size that definitely bigger than 10 nanometer, then required threshold can be lower. So before doing any experiment, actually with the simulation data, we kind of tested this hypothesis, and it showed that yes, if we can produce something around 200 nanometer, 300 nanometer, we can lower the required pressure threshold comparing to that existing gas pocket smaller than 10 nanometer. So further, we say that, and if we can kind of, because of this size, now we are going to make 200, 300 nanometer, if you have an idea about the tumor accumulation, it seems like these gas pockets or the nanostructure, if we can selectively accumulate into the tumor tissue, and so in that cases, which we call this the nano bump actually. So if I can put this bump only into the tumor cells, that when I apply the ultrasound, the cavitation threshold will be applied at the lower threshold, but only the region will get ablated is the location that where we have the molecular bump. And so then we will only remove this region. So you can think that this red color represents the healthy cell. They ablate only at high threshold. But where we located these nano droplets or nano agents, that of course they will be nano droplets initially. And so they are going to initiate the cavitation at lower threshold. So we will gain the selectivity in that way. So for that region, if we look at the literature, in that time literature was using this type of nanoparticles that initially has the perfluorohexane liquid in it for ultrasound imaging. So you can see in here they have a certain molecular weight, and like some of them you see it's that they are already gas at room temperature, some liquid at room temperature, but has a potential to be like a 29 boiling point, 37 can be gas. So, and good data that we know that they don't metabolize in the body. The perfluorocarbon that normally in the ultrasound imaging agent already is FDA approved and used in the clinic, that by just a simple inhalation, body can put them out. And we know that they have a temperature response based on the microbubble that people use for imaging agent. With the temperature, it gets expanded because it transforms to the gas, and under the ultrasound, they oscillate like that and give the signal. And so literature, and that time it was really popular, and it was around 2010, I think. And so people were trying to make an imaging agent, but nano-sized imaging agent. Micro-size was already on the market. They were trying to make the nano-size because we knew that because of the tumor's leaky vasculature, nano-sized any imaging agent can accumulate into the tumor, and they may help people to detect tumor early than the late stage. So then people were strategized different ways that initially they were designing this small nanoparticle that when they accumulate into the tumor, they may coalesce and make the big particle for the imaging. Why they were doing this? Because we know that the small nanoparticle, they are not good for imaging, but they can be good for the drug delivery or any other application. And somehow people they wanted to try the combination of it. But they figured out that the reason the nanostructure is not good for imaging, because this liquid they encapsulate inside the nanostructure wasn't transferred into the gas at the desired temperature, which was the body temperature. Because of this physics rule, the Laplace constant, the Laplace pressure gets increases. That simply, even if you have a volatile compound, if you encapsulate in a nanostructure, its boiling point just increases because of the surface tension. And so just simply, if you remember in the previous slide, I showed you 29 boiling point perfluorocarbon. That is this dashed dot one. And if you design something around 200 nanometer, you need to pass the temperature over 100 to make the liquid perfluorohexane to the gas perfluorohexane. So this is not possible in the body. And that was the reason, even though people structurally designed really nice nanostructure, but it wasn't working as an imaging agent. And so, but later they figured out the solution as well, which it really helped us, and acoustic droplet vaporization. They the temperature. They use ultrasound again to make this transition from liquid to gas. I mean, if you have liquid perfluorohexane and with the help of the ultrasound make it the gas, we call this acoustic droplet vaporization, and we rely this technique in our design, because temperature is not something I just explained, a tool for us to help whatever we want to reach. So we hypothesize that if we can design a kind of nanodroplets that has the liquid initially in it and and it can transfer into the gas when we inject it into the blood. And when we inject it, and because of the nanosize and the tumor's leaky vasculature, that that they have this gap between the endothelial cell that healthy cell doesn't have. And so nanoparticles, whatever we design as an agent, will accumulate into the tumor tissue. Then we can shine the ultrasound and cause expansion, or through the acoustic droplet vaporization, we can transfer liquid to the gas, and then we can use this produced bubble for cavitation. So with this way, we believe that we can lower the pressure, and this will give us the selectivity, because we will only accumulate these nanoparticles into the tumor because of size. You saw that in the healthy tissue, and endothelial cells arrange really tightly that this nanoparticle cannot go into the healthy tissue, that we don't have to worry about scanning the large region. If there is no particle, it won't ablate. So we can design this in a targeted version. I mean, we can make this nanoparticle that specifically recognize certain type of the cancer cells. So for that region, we first generation of our design that was the nano droplets. And I briefly would like to explain the nano droplets to you, that later you will see that now we have second generation of the reagent. But if you know the nano droplets, a kind of difficulties, even though they work very well and we really like them, still time by time we would like to revisit the nano droplets, but we needed something practical. So for the nano droplets, that's simply actually a polymeric micelle that made out of the amphiphilic block copolymer, has a hydrophobic and hydrophilic segments. That hydrophobic segment designed for, I mean, some of these blue monomers has fluorocarbon chains that interact with the perfluorocarbons. That's also fluorocarbon chain. And so, by the way, carbon and fluorine bond is the strongest and most inert bond in the chemistry. They don't react, they don't metabolize, and it's just a super hydrophobic. And so that's best agent for us. So we have this little thin shell in here. You see some of them, we stitched them to each other to stabilize this particle, that they're not gonna fall apart. And outer surface was PG, and that is a kind of increases the biocompatibility and a kind of prevents the recognition of the obstinate proteins for these particles. And eventually, with the chemistry of the PEG, allow us to target this or modify the surface of this nanoparticle by carrying the targeting agent for specific cell delivery. So as I said, that in the core, we have this liquid that represented with brown color. That's either perfluoropentane or perfluorohexane with two different boiling point that required acoustic droplet vaporization energy might be different for both of them. So we designed these nano droplets that actually, I'm not going to go really detail on the synthetic part, but if you want a kind of uniform the size distribution, that the used amphiphilic block copolymers molecular weight should be close to each other. So because of that, all these blocks, 3 blocks, they prepare with the controlled living radical polymerization that requires an extra work and a polymer chemistry knowledge or experience to design. It's not something you can buy on the market and combine them with each other. And so in the production way, that's just a simple micellization, but I can tell you clearly that it takes this process to produce final nanodroplets for 48 hours. And amphiphilic block copolymer, along with the perfluorocarbon, you dissolve it in a good solvent and add the bad solvent, and that triggers the self-assembly. Eventually, you remove the organic solvent which you don't want into the body, and finally, we cross-link it. So since this perfluorohexane is volatile, always you have to keep this solution in ice. It has a preparation difficulties in the laboratory scale. So, but when we use this for histotrypsy, which we call this nanoparticle mediated histotrypsy, I mean, instead of using existing gas pocket, now we put something that has the potential to be gas pocket or act like a gas pocket to trigger the cavitation that you can see in here. This is a kind of red blood cell phantom, a kind of gel embedded with the red blood cell and our nanodroplet. This is the before treatment, after treatment. When we have cavitation, I mean, one nanodroplet gets bigger and expands. You see them as this black dot. And when they burst the red blood cell, you see them transparent. Now it becomes white. So of course, we don't want to burst the red blood cell, but red blood cell is a perfect indicator for this study. It really showed that how we do it and how perfectly with the sharp boundary we can remove the tissue. So this is a kind of normal histotrypsy condition, 35 megapascal. See how big it is. But by using nanodroplets, we were able to do this at 11 megapascal. So yes, it is not as big as this one, but it doesn't matter. I can extend the treatment time as long as I am safe. Then I can still finish the tissue that I would like to ablate. For the selectivity, we embedded the nanodroplet in these hexagonal tubes, and now you can see in here the only this region that where the nanodroplet exists, there is cavitation, which represent these black dots. But between the two hexagonal tube, there is no cavitation, even the focal zone, which represented with the dashed line in here, doesn't show any cavitation. So this data shows that actually we can lower the threshold and we can selectively ablate the tissue by using NMH, I mean nanoparticle mediated histotrypsy. Even the top on all this information, right before ablation, we are able to see them. That's a kind of image guided ablation also that we were really happy about it. So, of course, I'm not going to go to detail, but we have studied nanodroplets a lot, like a half threshold and nanoparticle composition has changed. And you can see that we compare also the nanoparticle has pentane and hexane with two different boiling points, how they differ, is it same or not? And we saw that with the pentane, that has the 29 boiling point, which is more volatile. At some point, we have lost the perfluorocarbon in the system, but the hexane still 100 pounds later, we were generating the bubble cloud, and it was actively working in the system. So everything was perfect, kind of. Actually, we were planning to do some animal experiment. Actually, we had this melanoma model to ablate the tissue. My postdoctoral work, and so that I decided coming back to Turkey. And so, but still, since histotrypsy project is going on and very close to being in the market, it was in my mind always that even though I designed these polymeric nanoparticles for Pico nanodroplet, that was so difficult, and it was very difficult to compete with the histotrypsy when in terms of going into the market. So we needed something really practical that we can compete with the speed of the histotrypsy. Can anyone produce, easily produced? It's already FDA approved. And so I was just keep thinking about that, because as I say that nanodroplets was difficult to prepare and it required polymer chemistry experiences. It was, we used to obtain these nanodroplets like a milky solution like this one. And as you might know that all colloidal solution had certain extent stability, and the storage timeline is difficult and it requires cold chain because of it's volatile. And their size around 200, 300 nanometer. Polymeric micelles are not really big. I mean, you can control the size by the building blocks size, but 200-300 nanometer, now we know that every day smaller particle is better for deep tumor penetration. And the maybe biggest disadvantage for nanodroplets, we didn't know how much perfluorohexane we incorporate into polymeric micelle, because there isn't any way to calculate it. So just the random size of the balls you have, and each of them has perfluorocarbon, but how can you calculate it? So we simulated some stuff to make calculated, but it wasn't giving us a good data. Only thing we were arranging the dose of the nanodroplets in each treatment, we knew the concentration of the nanodroplets, saying that 5 million nanodroplets per milliliter was applied, but we didn't know how much perfluorohexane they carry. So our focus is maybe we can generate something as a second generation of nanoparticles that they can address all these limitations. So this is the nanodroplets, and now second generation we have something we call nanocone. That's a building block of nanocone cluster, which made up the beta-cyclodextrin, which is FDA approved, pharmaceutically commonly used compound that generally accommodates hydrophobic core to hydrophobic drug molecule and to solubilize the drug molecule for drug delivery application. So outer shell is hydrophilic, and so it has hydroxyl group in the secondary and primary phase. So, and the inner part, the gray part, is hydrophobic and can accommodate something hydrophobic if it matches with the cone dimension. So now we have something already FDA approved, like a perfluorocarbon, and why we don't combine them together. This is what we did actually, that you can see it was pretty practical. We just had the initially beta-cyclodextrin solution. Normally after 24 hours, till they stay as a solution, they don't precipitate, but when you add the perfluorocarbon, they form inclusion complex. This is what we call when the gas molecule goes inside the host. This is also host-gas interaction. And so they just precipitate it, and you can just filtrate and take it out. And this actually happens within 6 hours, and even though we kept it longer to increase the yield. And so it's pretty practical, like you mix A and B and obtaining the C. That's the best chemical reaction in the chemistry. And so, and also practical. So we were also able to determine the perfluorohexane amount because of this small compound beta-cyclodextrin. We used gas chromatography to determine the amount of the perfluorocarbon in every milligram of the nanocone cluster or this structure. So that was something really important for us because we will be able to compare the perfluorohexane amount and the dosage of the treatment. So later we proved that there is perfluorohexane in the system because by using the SEM-EDEX data, and also size you see in here, it was something around 50 nanometer, and of course size still varies, but we are able to tune it around 100 nanometer, which is smaller than the nanodroplets. So biocompatibility also, I can say that we tested they are not really hemolytic and not toxic for, this is the kidney, healthy kidney cell. And so how about the histotrypsy part? Is it gonna work like a nanodroplets or something limited? And you can see in here, this is the empty phantom. This is almost histotrypsy condition, and we apply 2 different concentration, which I can clearly tell you that the used perfluorocarbon amount is almost 100 times less from the nanodroplets in here, but still at 60 megapascal, we were able to lower the cavitation threshold. And so, of course, you can think that maybe nanocyclodextrin's empty cavity causes this. This is what we thought as well, and we tested empty cyclodextrin and perfluorohexane encapsulated cyclodextrin, that you can clearly see that this cavitation happens because of perfluorohexane. We have perfluorohexane in the system. So, of course, later we did more study to understand this nanocone structure better. For instance, since we know the perfluorohexane amount, we can clearly show that in the phantom, depending on the nanocone concentration, this cavitation threshold is really showing the concentration dependent behavior. Actually, we can tune this cavitation threshold wherever we want by playing with the concentration of the nanocone. That was something also useful for us here. You can see that this light gray line represents the normal histotrypsy, black represents the nanocone mediated histotrypsy, and you can see that with the increasing nanocon concentration, decrease in nanocon concentration, it starts acting like a normal histotrypsy. But we can, by tuning the concentration of the nanocon cluster, we can tune the threshold as low as 11 megapascal. So that was comparable with the nanodroplets. So if you remember, I showed you when we were testing the nanodroplets, that perfluoropentane encapsulated nanodroplets, we have lost the bubble clouds over the time. But here in the nanocons, we still have it after the 1,000 pulse. Even though we don't like this spreaded cavitation, we prefer something uniform, but still it shows that having inclusion complex is a kind of providing us the protection of perfluorohexane that's still in the system instead of evaporating. So that's all. Most of them are published work, but whatever I'm going to show it to you now, we have been working on it because we wanted to know more about that. So that's these clusters that we know that cyclodextrin by itself, it's almost 1 nanometer. And so we were getting something, first of all, precipitated. Visually, you can see it. That should be something around micron, right? And so when we redisperse it, we used to get collected as a powder. We keep it wherever we need it, we redisperse it and use it. And all histotrypsy data was obtained in this way. This is actually shows that our storage time, I mean, as a powder, you can sell it, you can store it. It's way better than a milky solution. So, but wherever we disperse it, it's something around 50 nanometer. That actually showed us that this is not just a single nanocon. It should be a kind of organization that puts everything together and gives us a size. And plus, we have this hydrophobic perfluorohexane in it. Sometimes we use one-to-one, sometimes we use perfluorohexane more than the beta-cyclodextrin. That should also differ on the structure of these nanocon aggregates. So in addition to this, cyclodextrin, even though we started with the beta-cyclodextrin, which is commonly used one, there are different analogs of it, like an alpha one made out of the 6 sugar unit, beta one made out of the 7 sugar unit, gamma 8 sugar unit, and they also have the different functionality. That functionality affects solubility plus the structure of this host molecule, that how it is going to accommodate the gas molecule. So because of that, we want to investigate this the computational study, since perfluorohexane is something only we can prove it by using EDX elemental mapping and gas chromatography, but that does not really give us a practical data, and it's difficult in each time to do so. It doesn't have any fluorescent, it doesn't have any UV that you can follow up, and also even NMR that requires spatial fluorine NMR. So we thought that computational data can give us a lot of information that we can match with or mimic the same condition and experimentally, that we scan actually all existing cyclodextrin derivatives by using molecular dynamic simulation. We noticed that with the perfluorohexane, depending on the perfluorohexane or pentane and how they form the inclusion complex, I can tell you that all of them forms the inclusion complex, but their stability is different. But only the gamma alpha cyclodextrin does not accommodate the perfluorocarbon in the structure in its cavity. Gamma sometimes accommodates 2, sometimes 1, and sometimes 1 goes in, comes out because of the cavity. So, and the next step, once we got the idea about the inclusion complex, how they form the cluster, we wanted to investigate that when they form the inclusion complex, those inclusion complex, since this hydrophobic tip of the perfluorohexane stays outside, a kind of with the free perfluorohexane, they have this arrangement that we call cluster, that we call nanocon cluster for them, that made out of beta-cyclodextrin perfluorocarbon inclusion complex plus free perfluorocarbon in the system. All beta-cyclodextrin derivative forms this type of complex, but alpha-cyclodextrin also forms cluster, but it doesn't form inclusion complex. It just forms a cluster around free perfluorohexane, but not really inclusion complex. And those type of complexes are not possible to precipitate and take it out. And most of the time, we have lost experimentally the perfluorohexane during the workup. But beta-cyclodextrin derivative, especially low-degree methylated and methylated one, allows and gives us a best nanocon cluster structure. Characterized for you for better understanding. Normally, beta-cyclodextrin, even though they have a clear solution, we know from literature that they have a potential to form aggregate because of the hydrogen bonding. And so in water, and when you add the perfluorohexane, they form this inclusion complex, and depending on the ratio of the perfluorohexane, if you use 1:1, and the most of them will be the inclusion complex, and but still they're like an aggregate. And if you have 1:5, you will have the free perfluorohexane surrounded with the inclusion complex that you can see in here. Initially during formation, we have maybe 400, 600 nanometer size, but later when we filtrated and redispersed it, we actually fall apart some of this aggregated cluster and get something smaller on the size. So of course, as the next thing that this question came to our mind, that so how stable they are going to be in the body, since they are just a cluster of, yes, there is a hydrogen bonding, and perfluorohexane are really hydrophobic and super surface tension that holds everything together, but we still wanted to see it. And so these are still going on studies, but experimentally we showed some stuff, but still histotrypsy site under investigation. And so what we did, we took the precipitated BCDs, nanocon clusters, we stir them, dilute them, stir again, dilute them, stir again. I mean, we really apply harsh stirring and dilution condition to see what will be happening in the body. So of course it is not an exact mimicking, there is no shear forces, other stuff in here, but at least it will give us an idea. And we saw that, and at the dilution and stirring conditions, still they are giving us a 50 nanometer, around 50 nanometer of the size, and perfluorohexane way better or stable than the perfluoropentane. So also, of course, pH is another parameter in the body, and in tumor it is different, and natural during blood circulation it will be different. We did a similar experiment with the pH dependency, also with the different pH condition, what will be happen with the stirring and the dilution. So you can still see that around 100 nanometer, they seems like a certain extent they are stable. So of course, if we want to compete and wanted to produce this as a product, and long-term stability is also important. So our aim is to sell this or make it as a product, as a powder. But let's say that user, they mix it, and what are they going to do the part that they haven't finished by using? And so they can store in the 4 degrees centigrade, or even at room temperature. We noticed that till 1 month they're perfectly fine, but like after 1.5 months, 2 months, they start still a little aggravating again, forming the bigger particle. But I'm pretty sure that if someone steer them, and again, they are going to come to that level to the initial size. But of course, we haven't tested this in terms of histotrypsy potential, how effectively they will work after 3 months in the histotrypsy. So that's still under investigation. The histotrypsy part of the stability hasn't completed that. Once we complete it, we believe we will publish it. So another study going on about it. So I say that our main motivation is something, a product, fast, practical, and that we can compete with histotrypsy. And histotrypsy as a just agent, it is fine, but most of the time people in the cancer treatment, they want to combine this treatment with the different treatments. I mean, they want to give some immunotherapy agents, some drug, or maybe they want to image it ultrasound way, or they want to target it. So we wanted to do this nanocon for practical agent for practical bioconjugation. So because of that, we prepared functional cyclodextrin like azide functional, alkyne functional, amine functional. These are the agents that they're having really practical chemistry and high yield chemistry potential, and like a click chemistry as an alkyne. Amine is for most of the bioconjugation you use amine functional derivative, and so we functionalize, we obtain the functional nanocon for that one, and we conjugate them, the different biomolecules. Like one, we conjugated peptide, we pegylate them, we conjugated folic acid, we conjugate the FITC. Just we show the different example and potential that's pretty practical actually, that you have already precipitated functional nanocon, like what I just showed is the for the regular nanocon. Whatever or people want to get it, they just mix them, they take their bioconjugate agent and mix them, and after that they centrifuge, take it and use it. That practical level. So I will just show one example to you. Again, this manuscript under preparation, that we have targeted EPPT is a kind of protein recognized the breast cancer cell line, and that has the already FITC labeled protein, and we prepared the FITC labeled BCD and tuned the fluorescent intensity. And so you can see in here the EPPT functional one goes more, I mean, cellular uptake is higher than the non-targeted FITC labeled BCD nanocons cluster. That you can see the differences in here. So we also investigate this for the flow cytometry or different application. But I just wanted to show one example to you, because we have an R01 NIH grant with the Virginia Tech University, Dr. Vilasiewicz, that's the collaborator. And so we have planning to do, by using this EPPT functional nanocon cluster on the breast cancer of mouse model. And now this will be the first animal trial of the nanoparticle mediated histotripsy, which we are going to use the nanocons for this purpose. So I think I finished on time. And so here you can see my collaborator and my group members, even though some of them are recently graduated. And so in this project from the Virginia Tech, we collaborate with Dr. Eli Vilasiewicz. And so Tanzil made the very initial publication on this project on the nanocon cluster, and Walid continues work in his PhD on this project. Erhan contributes time by time on this project. Cemran works on the nanofunctional nanocon cluster for bioconjugation. Betil works on computational side. Dilşah and Deniz, they were undergrad, but they did a really good work on the targeting nanocon clusters. And so I also would like to thank all the funding sources that contributes on my research, and also TÜBİTAK, that we have special grant for this project. Without financial support, there is no way we can do this work. Of course, students, I would like to thank to all of my students for their hard work. And thank you very much for listening. I will be happy to answer any question that rise during presentation.
Yasemin Hocam, thank you very much.
You're welcome.
Before Ceren takes the microphone, I want to ask a question. As a cancer biologist, first of all, you have such a big group, beautiful students, beautiful colleagues. You're so lucky to have them.
Thank you very much.
Congratulations on your work and your prepared manuscripts, which are on the way. My question is about these amphiphilic block copolymers. Have you checked the ATP levels after they're being included or integrated into the cells? Have you checked their ATP level?
No, we haven't. But these type of polymers, they commonly use actually, especially for the pegylated ones, since it's already FDA approved. Even though amphiphilic block copolymer has that hydrophobic part, might have certain extent toxicity, but it stays in the inner part, and we believe that this structure stays intact in the body. Because of the size, it just the surface is pegylated. We believe that they don't metabolize and body can eliminate them. Because of that, we didn't really look up the biological investigation for this particle. I mean, as a design and our proposal, it was working and we didn't really investigate that part.
Okay, usually because the copolymers, blood copolymers usually have an effect on the ATP level decreasing after being integrated into the cellular membrane. So the drugs that are interrupting can stay inside the cell. Maybe I was wondering, maybe your molecule also might have a similar effect. Maybe you can use them.
Might be, but I mean, I'm not sure whether it affects how they get into the cell, that how they interact with the cell membrane. It might be, but yeah, we haven't specifically investigated. I think whatever I say, it will be just my guess.
Okay, thank you very much.
Yes. You're welcome.
Jana.
We have one question about presentation. Mrs. Durmaz, I read on some articles about removing nanoparticles from body is not possible after used as a drug. I am wondering, what is your opinion about the problem?
So removing nanoparticle from the body, the challenge of it, I think this is the question, right?
Yes.
Okay. Yes, this is our research where we focus on. I mean, all these nanoparticle people keep synthesizing, and we even do the targeted version. And most of the time, I personally believe that they are so complicated. And research shows that, especially depending on the size, and there is a lot of parameter going on in the design. And yes, we design something that we believe they are going to be eliminated by the body. And there are research that clearly shows that they can eliminate it. But it really depends. Not for all particles, they can be removed by the body. First of all, the size is really important, how you decorate the surface, whether they can opsonize or not. Maybe during blood circulation, they just falling apart and you think that it is stable, but maybe you didn't, maybe they are not. And when they go into the cell, so what are you going to be to your particle? Is it going to fall apart in the cell or stays as a particle? Is it going to escape from endosome, or whether it will entrap in there? All these parameter, even though we have tools and practical way that accepted by the literature to address all these limitations, but personally I believe that on the paper it seems like it is perfect, in design it is perfect, but when it goes into the body it's not always working perfectly. But this shouldn't stop people trying, and now we will keep trying till find the best drug candidates. But I can say that nanoparticle based, there isn't a whole lot of drug onto the market. This is not only because of they're not working, it's because of this process is too long, like 10-15 years for a particle, that if everything goes well. So I personally think that design is really important, but we can't say that all nanoparticles are same and they entrap into the body. And we try to make it as best as possible, but still should be certain extent toxicity, because in the bottom line, all these are the synthetic material that we use them for our health or good purpose. But
yeah, thank you very much for answering our questions and your participating.
Thank you very much for invitation. It was really nice to be with you guys.
Thank you.
Okay, guys.
Thanks to Mrs. Yüksel for the presentation and her participation. Our next speaker is Professor Mustafa Ünal from the University of Texas. He's going to present us the assessment of bone matrix quality by Raman spectroscopy. And now I'll hand the line to Mr. Ünal. Thank you.
Let me just share my screen first. Here is that. So I think, yeah. So first of all, thank you very much for having me, and it's my pleasure to present here at the International BioMedTech Congress. And I also personally thank all the organizers of this great event, and hoping that the audience enjoying so far. So here is my presentation title, the assessment of bone matrix quality by Raman spectroscopy. So my current research focuses on two main topics. On the one hand, I work on identifying the regulators of bone toughness and bone fracture resistance and their association with aging and disease. I also work on the cartilage biomechanics in the frame of osteoarthritis. On the other hand, I work on translating Raman spectroscopy into the clinic. Let me just get this one. To improve the clinical assessment of fracture risk, as well as for early diagnosis of osteoarthritis. So actually, my today's topic is going to be covered more about our current efforts to translate Raman spectroscopy into the clinic. Actually, this part of my research. So here is the outline of my today's talk. So I will get started with the bone fragility and its effect. So then continue with the biomechanical testing of bone. Then lastly, I'm going to share our current efforts to translate Raman spectroscopy into the clinic. So let's get started with the question. So do you have any idea on how many bone fractures occur each year in the world? Of course, you have some number on your mind. So the correct answer is 10 million. So it's resulting a bone fracture every 3 seconds. So in terms of our country, this number was calculated as 24,000 in 2010, but it's only hip fracture. And 36,000 were projected for 2020, but I believe that this number is much more than this because this is only hip fracture. It's not covering all type of bone fracture. So in fact, bone fracture is one of the biggest health problems in the world. This is not only because of huge medical costs. This is also because of high mortality rate among elderly people, which is around 25%. Also, 33% of patients are totally dependent following a hip fracture. Therefore, the best strategy dealing with a bone fracture actually is the preventive fracture itself. Therefore, it is super critical to precisely assess bone fracture risk assessment. In fact, the bone mineral density measured by DEXA is converted to T-score. And T-score is the current gold standard for both diagnosing of osteoporosis as well as bone fracture risk assessment. So mainly, if your T-score is lower than a minus 2.5, meaning that your bone mass is 25% lower than a healthy one, so you diagnose it with osteoporosis and your fracture assessment is done. But the problem is that the BMD-based bone fracture risk assessment is not accurate enough to cover all population. This is because bone mass, or more specifically, bone mineral density, is only one of the factors of bone fracture resistance. And it can only, explain less than 50% of the variation in bone strength and fracture paths. In this perspective, if you look at the other factors included, one of them is that architectural properties, such as bone shape and geometry, and trabecular morphology, cortical thickness, and porosity. Another factor is material and matrix properties, such as the size of mineral in bone, the crystallinity, the amount of non-collagenous proteins, or the amount of water, including both bound and unbound water, as well as the quality of collagen, like collagen maturity, integrity, and cross-link. Therefore, in order to have a better fracture risk assessment, we should have as much as information from all these factors. So from the clinical viewpoint, the fracture resistance of bone is equal to the combination of bone mass, bone structure, and bone quality. But from engineering mechanics viewpoint, bone fracture resistance can be explained with different mechanical properties of bone. For example, bone fracture resistance can be strength, toughness, fatigue, creep, or fracture toughness. This is because none of the, actually no, none all the bone fractures seen in the clinics are associated with the similar biomechanical failure mechanism. For example, if you look at the osteoporotic fracture, it's actually generally associated with the low strength. But on the other hand, if you look at the atypical femoral fracture, seen in the clinic, especially after a long-term drug usage, is associated with the low toughness. And if you look at the stress fracture, generally happen on the spine, is associated with the low fatigue. As you can see, 3 different bone fractures actually are associated with the 3 different biomechanical failure mechanisms and associated with the 3 mechanical properties of bone: strength, toughness, and fatigue. Therefore, in biomechanical field, we are using different types of mechanical testing to characterize bone quality or material properties of cortical. So among them, tensile test and the 3-point bending test are among the most commonly used one. And for this, the mechanical testing, first of all, we need to prepare a special specimen, like, the dog bone shape, as you can see here, or a rectangular uniform beam, as you can see here. So then, we just load this, the specimen under load and until they break, and resulting a graph we call stress-strain curve. So using such graphs, we are able to calculate different material properties or bone quality parameters, such as toughness, osseous strain, elastic modulus, yield strength, or ultimate strength, or so on. So actually, all these mechanical properties are the true way of the characterize bone quality. So on the other hand, the fracture toughness is the best way to mimic in vivo bone fracture. This is because all material, including bone is also, a composite material, have flaps, the crack in this, the perspective. So here you are seeing a bone surface, and as you can see clearly that there's like, a linear microcrack located in here. So this is, the common thing. So during our daily activities, like, the walking and running, our bones are under repeated load and stress. And this load and stress causes microcracks on the bone surface. So for healthy one, for the healthy person, this is not a problem because, the mechanism we call bone remodeling is like, easily can happening and repair such, microcracks located in here, especially and timely manner. But when for unhealthy bone or when we get older, this repairing process takes much more time. Therefore, such microcrack can serve as the origin point of the bone fracture. So the bone fracture can start from such microcrack timing. So in this perspective, the fracture toughness is the measure of the ability of any material to resist crack initiation and propagation. So for example, you can say the rat femur under a fracture toughness test. So when we put the microcrack located in here, and we load this rat femur, you can see that the crack propagation, initiation and propagation is happening. So actually the fracture toughness is the measure of the ability of the resist the crack initiation and propagation. This is important in our perspective because healthy and unhealthy bone completely behave differently, under fracture toughness. For example, if you look at the healthy bone, crack initiation is very hard, and crack propagation is also, takes time and has the zigzag pattern, as you can see. It is very hard also for crack propagation. But for the unhealthy bone, as you can see in here, crack initiation is sudden, and it takes, very quickly, and has the linear, as you can see, the crack propagation. So as you can see, very differently, the behavior under fracture. So again, in order to have better fracture risk assessment, we should have as much as information from all the factors determining bone fracture. In this perspective, luckily, the DEXA, computed tomography, MRI, and the ultrasound can readily provide an information about the bone mass and bone architectural properties. But the problem here is that there is no medical technology currently that can provide us bone quality measurement in vivo. That's the problem. So therefore, in order to have the best fracture risk assessment, we should have to find a way to get information about bone quality. In fact, mechanical testing is the true way of getting information about bone quality, but they are all destructive, including fracture toughness. So therefore, fracture toughness is not clinically viable technique. So I mean that you cannot to get this big of piece of the bone from the patient, just go to the lab and test this the bone specimen on the fracture toughness. This is not viable. This is not feasible. So therefore, what we need we need to develop a surrogate clinical measure of bone's fracture toughness, or in general, the mechanical. So in this perspective, we believe that Raman spectroscopy is very suitable tool for this, the purpose. So why Raman spectroscopy? First of all, Raman spectroscopy is a non-destructive and non-invasive method. It's also, we don't need any sample preparation, but the uniqueness of Raman spectroscopy is that Raman spectroscopy can characterize all three main components of bone, namely mineral, organic matrix, and water, simultaneously, non-destructively, and non-invasively. That's very important. Also, except Raman spectroscopy and MRI, none of the methods is currently capable of measuring bone quality in vivo. Therefore, Raman spectroscopy is very suitable for such clinical tools. As you can see here, it's the couple of Raman spectroscopy in terms you are not familiar with Raman spectroscopy. A Raman spectroscopy that we use in the lab is generally integrated with a microscope, as you can see here. And here are the three big brands on Raman device. So if you look at a typical optical setup of Raman spectroscopy, we always use a laser source, and generally we use 785 or 830 nanometer wavelength. So then we are using such optical setup to transfer the laser onto the bone. When the laser interact with the bone, it causes a vibration on chemical bonds. Then this vibration, causes a measurable shift in the wavelength of scattered photons. And these scattered photons are analyzed by a spectrometer. And the outcomes of Raman spectroscopy we call Raman spectrum. As you can see here, a graph, we have an x-axis and we have a y-axis. For the x-axis, we have a wave number, and in the y-axis, we call it intensity. Actually, it is the number of collected scattered photons. So actually, any Raman spectrum is specific to a material, I mean. So for example, if you look at this Raman spectrum, this is specific to bone. If you are seeing this Raman spectrum, you can easily say that, yeah, this is coming from bone. Because, each peak location on a Raman spectrum is kind of the fingerprint of any material. So currently, there are two main barriers in front of the translation of Raman spectroscopy in the clinic. Actually, there are more, but this is the most, the important part. The one is that if you want to, transfer Raman spectroscopy into the clinic, first of all, we need to validate that whether Raman spectroscopy can distinguish between strong and brittle human bones. And secondly, we need to find a way to develop a Raman spectroscopy, which is a clinically viable Raman spectroscopy that can collect a bone signal in vivo through the CT. So let's get started with the first barrier and what we did and what the others did to overcome from this barrier. So here is the typical Raman spectrum of bone, and generally it is reported between 800 and 1800. And as I said before, this is a typical Raman spectrum of bone. So if you see this spectrum, you can easily say that, yeah, this is coming from bone, because there is the specific peak location is associated with the bone. For example, the most prominent peak is the phosphate peak located in here, like 960. So this phosphate peak is associated with the mineral part of bone. Another mineral part of peak is carbonate in here. We also the several other Raman peaks, like the proline, Mi3, CH2, and Mi1, all associated with the collagen or organic matrix. So during the past 2 decades, several researchers, including mine, have developed several the Raman measures. We call sometimes we call Raman measures, sometimes we call Raman properties, or Raman indicators, or Raman biomarkers. So there are different the name, but let's say Raman biomarkers. Okay? So several researchers, including mine, developed several biomarkers associated with bone quality measures. For example, For example, the intensity of the phosphate peak here is divided by any of the organic matrix related peak. It could be proline, amide3, CH2, or amide1. Is associated with the bone mineralization, or we can say that bone mineral density measurement, but at local level. Another, for example, the bone biomarker, bone Raman biomarker, is like the carbonate substitution. So as you can see, we have a carbonate peak located in here. The intensity of this carbonate peak divided by the phosphate peak provide us information about mineral quality. Another mineral quality measurement is the full width half maximum of phosphate peak, and it gives us information about crystallinity or another the mineral quality measurement. As you can see, there is a small peak located in here. Although it is a small, it is this small amide1 peak is specific to collagen, and we get many the important information about this amide1 bond. So as you can see, actually this the small peak is made up by 4 underlying peaks, as you can see here. So in the past, some researchers found that this 1668 to 1688 ratio is associated with the measure of enzymatic crosslink in collagen. Actually, enzymatic crosslink have an essential role in the stability of collagen material. And more recently, I developed another Raman biomarker, and I'm going to talk about it a little bit later. But as you can see, using conventional Raman spectroscopy, there are several Raman indicators associated with the bone quality. And in the past, we found that, we and the other researchers found that this Raman measure or biomarkers significantly change with the disease. And also, drug treatment, as well as, they correlate with the selected mechanical properties of rodent bone. But today, there is no consensus on which Raman indicators or biomarkers are most sensitive to fracture resistance of human bone. This is the important point because there are some differences between human bone and animal bones. Therefore, we need to validate that whether Raman can distinguish between weak and strong of human bone. So before moving on, I would like to highlight my ratio. Actually, this is the 1670 to 1640 ratio, but unofficially it's also known Unal ratio based on my surname. So what I found during my doctoral study, that collagen is abundant in our body, and all the part of our body is actually mainly composed of collagen, different types of collagen. And this collagen it is original triple helix structure. So what I found that when these collagen molecules denaturate, it could be thermally or naturally. It transfer from its original triple helix structure to a random structure. Then I observed that this, the amide1 ratio that I call 1670 to 1640 ratio is increased. The more importantly, what I found that when this ratio is increased in a bone that we test, the toughness value is decreasing. The toughness is very important mechanical property of bone and is associated with bone fracture resistance. So at the end of the day, what I found that this 1670 to 1640 ratio or Unal ratio, whatever we call, is associated with collagen secondary structure or denaturation or the collagen integrity status. So if there is something change in the helical structure of collagen, then we are seeing that this, the ratio is increasing. So fiber optic Raman spectroscopy is an emerging field, especially diagnosing diseases such as cancer, and it is actually the clinically viable version of Raman spectroscopy that we use in our labs. But the thing is that along with involving different optical setups, there are also a number of differences between fiber optic Raman spectroscopy and a regular Raman spectroscopy. For example, fiber optic probe Raman spectroscopy does not preserve inherent laser polarization. It's an important issue. Also has a laser spatial and spectral resolution, also has no confocality. Therefore, whatever we develop using this Raman spectroscopy at lab are not necessarily measurable with the fiber optic Raman spectroscopy because of this difference. And to date, actually, there is no evidence showing that fiber optic Raman analysis predicts mechanical properties of human bone. This is an important thing if you want to, because in the clinic, most probably we are going to use this kind of setup. So first of all, then we need to validate that whether the Raman biomarkers that we collected using this fiber optic Raman spectroscopy can predict mechanical properties of human bone. For this purpose, what we did, we collected 58 fresh frozen femur from the cadaver, and we prepared single edge-notch beam. Then, we just calculate their BMD values and porosity. Then we tested, the specimens under fracture toughness. Then what we did then? We collect Raman spectra using both, the confocal Raman microspectroscopy. It is a research-grade Raman spectroscopy that we are using at lab. And also we use, the spectra using a clinically viable version of Raman spectroscopy. Our aim was that whether this, the data collected using the fiber optic probe-based Raman spectroscopy can predict mechanical properties. This is an important, point for this, the research. So at the end of the day, regardless of the, the Raman spectroscopy that we use is a lab tool one, like Raman spectroscopy, regular conventional one, or fiber optic Raman probe. So, or Raman, the biomarkers significantly correlate with the fracture toughness properties of human cortical bone. And this, the predictive power is around the 50%. But among all the, the Raman biomarkers that we tested, we found that phosphate to amide-1 ratio, which is associated with the bone mineralization, and my ratio, the UNAL ratio, the 1670 to 1640 ratio, actually explain the highest variation in bone fracture toughness. I mean, the highest, they provide highest RCQ value. So indicating that, so this two, the Raman biomarkers can be a target, the in vivo Raman biomarker that we're planning to, the check in the near future. So, or this result also, the show another important point. This one was that, the BMD, which is the current, the gold standard, and aging can only explain 12% of the variation in fracture toughness. And it's actually, the predictive power, we can say that, 12%. But Raman itself can, explain the 50% variation of the same mechanical properties. And these all results, they actually, highlighting at one point, Raman can distinguish tough and beautiful bones. So then, our current research and the previous studies cumulatively, indicate that Raman spectroscopy can distinguish between strong, tough, and between strong, tough, and brittle and weak human bones. That's the important thing. It looks like we just, overcome this, the barriers. And the second barrier is that we need to, to develop a method that we can collect Raman spectrum in vivo through the skin and non-destructive manner. So more specifically, we are seeking an answer of, can we really measure UNAL ratio or other Raman measurable biomarkers in vivo? The answer is maybe, because, all is about whether, the laser can reach the bone, because Raman spectroscopy is a laser-based technique. So if you want to collect a Raman spectrum, then first laser can reach to the bone, right? So in this perspective, if you look at the depth of laser penetration in bone tissue, it depends on the wavelength of laser. So for biological samples, we generally use 785 or 830 nanometer laser wavelength. So for this kind of laser wavelength, it looks like laser photons can travel up to 67 millimeter in depth in our body. It means that if you choose a suitable region of our body, it could be like, for example, tibia. If you check your tibia, you can see that, or our fingers. It looks like we can, collect in vivo Raman spectrum non-destructively and through the skin. But another barrier is that the current Raman setup that we are using our lab is like, this kind of arrangement. So we are sending laser and collecting scatter photons from the same spot. That kind of arrangement doesn't allow photons to go to the deeper region. And actually, we are collecting backscattering photons. And that kind of arrangement only allows us to collect Raman signal up to 5 microns in depth. Then this is not feasible. So luckily, in 2005, a new Raman method we call spatially offset Raman spectroscopy was invented by a UK research group. And in this Raman setup, they are sending laser from different points, as you can see here. Then they put some special offset. Then they are collecting scattered photons from here. And that kind of arrangement allows photons to travel to more deep region or body and increase the chance of to get signal from bone. So therefore, we decided to check whether we can, to collect Raman signal using this source method. For this purpose, we just, conduct a phantom study. So basically, what we did, we prepare chicken meat slice. Each one is like, the 1 millimeter thickness, and just like we are mimicking or skin or like other soft tissue, because the chicken meat also or skin and other the soft tissue, all including collagen, like the same main component. So therefore for the easy process, we just choose the chicken meat slice and we prepare each one is like the 1 millimeter. Then we have a real human bone, as you can see. We get the real human bone from one cadaver. So what we did that we just put this the chicken meat slice like one by one on the top of the bone specimen that we test. Then we try to reach the bone signal. So for this purpose, here is already the optical setup. We have like the one fiber optic cable, as you can see here, and we are sending laser. At this point, we are using 785 nanometer. Then we just manually determine this offset, and we have a like collection fiber, as you can see here, and we are collecting scattered photons from that. So at the end of the day, what we saw that, depending on the skin, in real case skin, but in our case is the mid thickness. So we can collect bone signal up to 1 centimeter in that. That's the perfect thing. But depending on the special offset, it can be like the 8 to 20 millimeter, and again it is depending on the chicken meat slice thickness. So maybe you are just thinking right now that how you make sure that you collect Raman signal of bone. Yeah, that's the natural question. So we know that because here let's look at together for this the Raman effect. So here is like we use 5 chicken meat slice. It means that we put the 5 millimeter chicken meat slice in thickness on the top of the ore bone specimen. So before that, we just go and collect Raman spectra of bone, and it is like the top of the Raman spectra, as you can see. Then we just put this 5 millimeter thickness chicken meat slice on the top of the bone, and we just like play with the offset. So the 0 millimeter offset, meaning that is side to side. Then we put 5 millimeter and 8 millimeter. As you can see, there is a like the peak located in here. This is called phosphate peak. This phosphate peak is specific to bone. So if you are collecting this, the peak, it means that you are collecting data from bone. It's like the perfect thing for us. But the problem here is that although we make 100% make sure that we are collecting bone signal from the mineral part of the bone, but other part of the Raman spectrum, for example, MI3, CH, MI1, and proline can be the combination of both bone and chicken meat slice, because both chicken meat slice and bone has a collagen content, right? But at this point, still, we don't know how, like, we don't, 100% sure that all the data we are collecting is coming from the MI1 of bone. So as summary, our current study, and as well as, the many previous studies, we just show that, and along with the previous studies, Raman can distinguish between strong and weak bone, which is highlighting the potential of Raman spectroscopy as a potential need critical tool. But still, we need to optimize this source technique. I mean that still we need to optimize the special offset distance, as well as other parameters, such as laser power is very important parameter, because a huge laser power can damage tissue, including our skin. Also, as I said just recently, source MI1 is not specific to bone at this point, because in real case, skin and other soft tissues also contribute to the signal. But in order to have unal ratio, so this is the 16.7 to the 16.4, and it's associated with the MI1 bond. So we need to find a way to extract pure MI1 signal, or at least we need to to validate that whatever we are collecting is mostly associated with the MIT1 of bone, not like the soft tissue. So as a future direction, so currently, our ongoing effort is like, this was part of the research. So we are currently using non-invasive special offset Raman probe, and we are trying to get the signal from the human in vivo through the skin, and our specific region is the tibia, because even you can, touch yourself and see that bone is just there. So this is a suitable region for us. But also we are planning to, using a minimally invasive needle-based fiber optic probe. As we, in this, the case, we have a needle, as you can see, and we are just inserting fiber optic cable inside of this needle. But this kind of arrangement can, help us to reach deep region. For example, the hip or the femur. But both ways, at this point, we don't know. But in near future, we believe that clinically viable Raman spectroscopy can definitely improve the patient-specific prediction of fracture risk. So that's the current effort. So I would like to finish up my presentation with this beautiful African proverb that I like. So if you wanna go fast, go alone. If you wanna go far, go together. So this research, of course, wouldn't be possible without the great mentors, collaborators, and funding. So I acknowledge all of them. So again, thank you very much for listening to me, and I can get any question. And please also do not hesitate to contact with me through my Twitter, my Instagram, even my LinkedIn. So again, thank you very much for listening to me and attention.
Mustafa Hocam, thank you very much. It was a very interesting talk, actually. I've had some sort of connection with Raman spectroscopy in my PhD student time, well, PhD time, but I never actually got into that field of science. But it was very nice and interesting to hear from you. And plus, this ratio, Ünal ratio, is actually quite a good name. You came up with your own name. That's great, actually.
That's good. Actually, the official is known the 1670, 1640, but when just, go to one conference and they are said, oh, the ratio. They are just unofficial name of my ratio. Based on
it's much better than the numbers, definitely.
Yeah, that's
so
correct.
I actually have one question before the other questions, if you don't mind. I was also interested in one of the diseases very related to bone disease, actually, it's hernia. It's where you lose the chondrogenicity in your spine. So I was wondering if this Ünal ratio applicable, or Raman spectroscopy methodology applicable to measure the chondrogenicity of nucleus pulposus, jelly substance in our spine, our vertebrae. Because it's also rich in collagen.
Then the answer is yes, because if we are seeing any change in the structure of the collagen molecule, then this Ünal ratio give us some the differences if you like to compare to the health one. So definitely this 1670 to 1640 ratio is applicable to not only just bone field as well. So since our body is made up of collagen molecule, so you can it is applicable to all other fields. So I believe that in near future, this ratio will be used more broadly in different fields as
well. In terms of the material that you actually observe on the Raman, is it better to go with the tissue for the disease that I'm just talking about, or the cell line, the cells maybe?
So for this, especially the tissue one is better, because for the cell one, you need another technique we call surface enhanced Raman spectroscopy, because it is very hard to get the Raman signal from a single cell level. So we need another we need some enhancement, because it is really hard to get the Raman signal from a single cell. But for the the tissue level, it is easily. You don't need any the sample preparation. You just go and shoot the laser on your tissue. Then you can get this MIT1 band, and you can calculate this or 1670 ratio. But for the cell level, you should definitely think about the SERS technique, surface enhanced Raman spectroscopy.
Does it matter how thick the tissue is?
So of course not. That's the nice thing of Raman spectroscopy, because even you can get the signal from very thin or very thick specimens. But the opacity is important. So the thickness is not a matter. But again, some biological tissues may have a fluorescence problem. I am not sure about your tissue at this point, but if there is no fluorescent issues, I think the thickness is not matter, doesn't matter.
Okay, well, I'm done with my questions. I think our moderator can take the microphone now and ask if there's more questions. Thank you. Thank you very much.
Thank you. Thank you for having me.
Thank you for your presentation. We have a question about the topic from our member. Someone asked, you are working on the relationship between structures such as bone and cartilage and orthopedic diseases. What led you to do research on these structures?
So for example, for the cartilage, the research is focused on the water content, and basically because the cartilage is composed of mainly water, like 7 to 8% of the cartilage is made of water. So for the cartilage, I'm specifically working on the role of water in osteoarthritis, and also how this the water change can have an effect on mechanical function of cartilage, because our cartilage has the role of the mechanical function as well. So for the cartilage, more specifically, I am working on water content rather than collagen and proteoglycan.
Okay, thank you. That's all.
Thank you very much again for having me, and it's my pleasure to
You're
present
welcome.
here.
Hello, everyone. In this session, we have Dr. Fatma Patlar Akbulut with us. She received her bachelor's and master degrees in computer engineering and doctoral degrees in bioengineering and biomedical engineering. She continued her postdoctoral study at North Carolina State University. She carried out the development of low power wearable sensor system and ultra low power sensor array studies. Currently, she is an assistant professor at the Kültür University. And today she will tell us about wearable technologies and healthcare. Before starting, I would like to thank you for your great kindness and for sparing your valuable time for us. And as a reminder to our participants, if you have any question, you can write in the chat section. There will be time for a question at the end of the session. We will address your question to Dr. Akbulut. Now I'm leaving the word to you, Dr. Akbulut.
Thank you. Thank you. Good afternoon, everyone. Thank you for having me today. Like I said, I'm going to talk about the wearable technology and healthcare today. Let me show my organization. My talk is organized as follows. First, I would like to start with the introduction to wearable technology. Then proceed with the sensor systems, which are super critical for this concepts. And following that, I will show some state-of-art products under this category, and ultimately present my 3 research papers to give you a gentle introduction of utilization of such systems in R&D projects. So in the recent years, the wearable technology has seemed to explode, as you can follow. So today fitness bands, earphones, earbuds for music and the smartphone use and smartwatches are dominant product types in our lives. And this figure depicts the broad range of application and function of the wearable technology. And as you can see, the application domains are not limited to the medical domain. Also includes sport, wellness, business, security, and many more. So we will focus on medical health part today. And as you can imagine, there has been potential, there has been exponential growth is the use of the wearable technology. And these are now considered to be critical importance in the certain consumables and the service sectors, including the especially healthcare. And today, the term wearable goes beyond the traditional definition of clothing. It refers accessory that enable the personalized mobile information processing. So this means wearable technology in healthcare are undergoing a shift from simple being fitness tracker to real-time clinical monitor. And so let us start with defining what is wearable technology, what is wearable device. Wearable device simply defined as monitoring modality that is worn by a user in daily life. And it refers to some smart electronic device that are worn by the body to evaluate and transfer various types of data, such as signals and signals related to the human bodies. And we can say that physical activities. So it's very popular these days, and the market shares show this popularity to us. And a market share of the wearable system shows the impact of this device. So in the early years, most growth occur in the low-price fitness tracker markets. And more recently, devices such as smartwatches, smart clothing, and new generation smart glasses are gaining the share, and it's kind of attracting the new audience. And in the worldwide, in today's world, end user will spend on wearable device total, we can say that 81 billions in this years by this year. So this means 18% increase from the previous years. And these rise in the remote work and the increased interest in the health monitor during the, we can say that COVID pandemic was a significant factor in the driving market growth. And this is not the and this is only beginning. We can say that. So as the device market focus on improving the sensor accuracy, and by improving the accuracy of this sensor, the performance gap between the medical and the non-medical grade wearable is closing, and driving to grow in the multiple wearable device categories. And the capability of these kind of device, this embedded sensor device, is often determining the factor in the reliability and the usefulness of the wearable products. And the given sensor improved transients over the last several years. And sensors, these embedded sensors, built in the wearable device will be increasingly capable of the more accurate ratings. So we can say that in maybe 3 to 5 years, the market continue to grow more rapidly. So of course, some of the devices will be getting smaller, and also having influencing factor in the wearable market by enabling these device markets to integrate the sensors into some kind of wearables. And these kind of wearables are nearly invisible to the end user. Sorry. And day by day, we are making these devices smaller and smaller, and the continued advance in the miniaturization and integration will be enable the further use case and benefit adoption of this smart devices or printed devices or ingestible, and the we can say that of course smart patches. And we have lots of opportunities. So while wearable technology have been widely cited as the effective approach in the healthcare, especially in these days, in these COVID emergence of the COVID, presented opportunity to use these kind of devices, to use these kind of wearable devices to contain the spread of the disease. And those very wearables have the potential to provide the real-time remote monitoring. And even we can say that symptom prediction to support the medical diagnosis and treatment based different physiological data. And we can use this opportunity, especially in these days. But the success in the technology is not still absolute. Still challenges still exist. So including its reliability, some kind of standardized measurement and setting up the range of the data for the correlation with the patients, and for the assessing different actions for treatment. And these are not all the challenges, but the most important ones. And these have also been significant challenges in making the fundamental improvement to existing mechanical, electrical, and optical sensitive models, especially in improving their specificity of the detection. And many of these challenges can be understood by the, let's say, appreciation of the body surface as more of the information barrier than as the information source. So skin will be critical for us. So understanding the skin structure and its response to different type of sensing is necessary because these understanding the skin structure help us to remove the scientific barriers, so we can design more efficient and maybe even more robust skin sensors. And of course, wearable devices in our daily life, but especially in the medical area, it's there's an increasing demand in the use of the medical devices. So wearable medical sensors, we can say that present exciting opportunity to measure human physiologic parameters in the continuous and the real time. So this can lead us. This latest advance has seen these devices now capable of collecting highly accurate health data and connect remotely to the personal physician. So he will then be able to monitor your health progress and also check if you are correctly using your medication. And also we have a typical example of trending medical wearable, including the Google Smart Lens, health patches, and etc. So these come with the patches and the sensors that are capable of detecting the body change and analyze the data and cautions in the individuals of the developing disease. So this can be critical for us. And the one key advantages of the wearable medical devices is they may know when we are sick before this. So the continuous monitoring means that are a lot of data available for establishing the user baseline. So it means for this we are using a lot of sensors, and these sensors incorporate broad range of methods in the, we can say that micro electromechanical, biological, and even chemical sensing. So it means we can measure a lot of signal. We can measure and analyze various vital parameters such as electrocardiogram, blood pressure, body temperature, respiratory rate, and many more, and provide medical professions while making diagnosis or monitoring chronic medical conditions. So some wearable can even predict when patients might begin exhibit symptoms before having actual situation. So these has led to development of the commercial handheld sensors for the measuring and the monitoring. Also, we are developing some prototype. And now I want to mention about these kind of prototypes. So I will talk about the utilization of the wearable systems in the academia and the R&D projects. I would like to start introducing my recent works with the paper titled "A Smart Wearable Device for Short-Term Cardiovascular Risk Management with the Emotional Dynamics." In the study, a wearable system design called cardiovascular disease monitoring, which provides continuous medical monitoring and creates health profile with the risk of the disease over time. And systematic tests were performed with the analysis of 6 different biosignals from the different test groups with 30 participants. Half of the participants have some heart conditions and half of the participants were the health well. And during the test, in addition to the examining the biosignals of the patients using the physical activity results and stress level deduced from the emotional state analysis. And these, with the emotional state analysis, achieve a higher performance in risk estimation. So, and in the study, we design and develop a smart wearable prototype. And our aim was to analyze and detect short-term risk of the heart and the circulatory system with the 6 medical sensors, namely ECG, body temperature, pulse oximeter, galvanic signal response, body blood pressure, and glucometer. And we collect the real-time biosignals from the subject. And to collect these physiological data, we develop a mobile application. So this figure shows the interaction of the all components with each other. And okay, so our wearable multi-sensor e-health device is shown in this figure. So the developed prototype incorporates an ECG, body temperature, pulse oximeter, galvanic signal response, blood pressure, and the glucose sensors. So for all measurements, the microcontroller coordinates the data transfer, and the measured data is stored in a cloud interface where it is analyzed. So and ultimately we have gathered a data set of 30 participants, demographic informations, biochemical blood results, and the physiological data of the 6 different biosignals from our wearable device. And with the study, we show that the interpretation of the biosignal will lead to high level of health status prediction when we support our system with the emotional dynamics. So it means with the measurement made with the galvanic signal response sensor, and it can be estimated which patients are mostly similar to which emotion to use the treatment of the patients. So because negative feelings has an effect on the cardiac and the circulatory system. So that's why we try to build a system with these emotional support. And we reach a high accuracy with the help of the emotional dynamics. And in other work of ours, we use previously collected data sets to evaluate the stress level of the metabolic syndrome patients. So here, this study presents a multi-variate methodology for modeling the stress on the very specific group, which is metabolic syndrome patients. And we have developed a supportive system to cope with the MAS patients, anxiety, and stress by means of several biosignals, such as the ECG galactic response and the other sensor readings, such as the oxygen saturation and glucose level, and that are measured by the wearable device, again, with our prototype. So in this study, additionally, we employ a neural network model to classify the emotions in the detection of the stressful moments. So we have accurately recognized stressful situations using the physiological response to stimuli by utilizing our proposed affective state detection algorithm. And by the help of this algorithm, so before mentioning about the results, the focus of this paper is dedicated to metabolic syndrome, or simply we can say MAS patients. And first, let me explain what is MAS. So MAS is a group of disease in which more than one cardiovascular disease risk factor is clustered. So MAS describe a high-risk population having 3 or more of the clinical characteristic of this table. So the reason selecting of the MAS patients is the how to say, so the influence of the psychosocial stress on the MAS patients is seen as more damaging than healthy individual. So that's why we select this focus group. And for the experiments, we collected data under 3 stages, as shown in this figure. And the average data collection time from the participant was 1 hour. So we can say that the most challenging part of the biomedical studies is to collect genuine data. So alternatively, you can use the public data sets, but the more proper way is you are getting your own data. So anyhow, first participants were examined by the physicians and created a case file, and that contains general information of the patients. And in the following stage, the participants asked to perform 3 activities while we're collecting the vital signs with our wearable sensor device. So biosignals were collected under 3-phase experiment plan, such as resting, watching the video, and during an activity. And during the measurements, all participants were asked to provide the demographic information such as the date of birth, health status, including the blood results and other kind of informations. And in the experiment part, in the triggering the emotion part, we use different videos to trigger emotions of the participants. In the video intended to induce the calmness emotion, we show the participants the nature images and underwater shots. So the effect was enhanced by some background music. And to trigger the fear emotion, we show the participants horror scenes from several horror films. And for the sadness, we show the participants the emotional movies, emotional drama films. So for the anger, we choose we show the participants a baby being beaten by his caregiver and people being beaten unfairly by police. And for the disgust emotion, as you can see, we use some scenes of eating insect and bad animals and these kind of videos. So finally, to induce the happiness emotion, we show the participants cute animals, babies, and these kind of video clips. And here, the only exclusion criteria were applied to participants who close their eyes for a long time while watching the videos, and the rest of it we just collect all the information. And okay, to address the needs for pre-processing and transmitting the data of the wearable system, we have developed e-health mobile application called the Stress Observer. And this application is designed to run on the Android-based mobile devices. So I will not give much detail for the time issue. Okay, ultimately we have proposed a stress model that includes the affective state detection algorithm. Our proposed system achieves high accuracy, classifying the stress level of the all patients. And we can say that it's important for the physician to determine the stress level with the high accuracy, so that the mass patients can achieve precise stress management therapy. So maybe they can use a supportive model in clinic. And as the last paper of mine that I would like to mention about the emotion recognition from sensor reading. So until now, I tried to use emotion in most of my study, but here we use a different methodology to recognize the emotion. We target to catch the change in electrical property with the electrocardiogram and the electrodermal activity, because these signals are impacted by the peripheral nervous system of the body, and the peripheral nervous system is the strongly coupled with the mental state of the person. So this time we use different technique to identify the exact emotion. And okay, it's widely accepted in the literature, if you are dealing with the emotions, the emotion can be classified into 6 main categories: the happiness, sadness, surprise, fear, anger, and disgust. And different theories have proposed diverse categorization of emotion, such as stable. And among these 6 emotions, happiness is the most important representative of the positive emotions or positive feelings. And it emerges in situation where the individual are most comfortable and life experience are most intense. And it has been observed that the individual take action to maximize the possibility of feeling positive emotion and minimize the feeling negative emotion. So the experiments on evaluating the accuracy of our proposed method are conducted on 3 levels. In the first level, we simply classify whether emotion was positive or negative. And in the second level, we find out exactly which emotion is experienced by the participant without using results from the first level of classification. And in the final step, in the third level, we perform hierarchical classification, where we first classify a given sample into either positive or negative affective state, and then further identify the exact emotion within that affective state. So, and the classification at this level can be useful in the telehealth systems, especially to identify if a patient has been experiencing negative emotions, so that the physicians can take the proper steps to maybe mitigate any negative impact of the persistent negative emotion. So the application area of the so wide, that's why we are analyzing in different ways. So in the study, we have presented new and accurate method to recognize 6 different emotions using 2 biosignals, taken with our variable sensor prototype. And okay, this concludes my presentation. If you have any question, I can have now. Thank you for your participation.
Fatma Hocam, thank you. It was a very interesting topic. I'm not really familiar with the technology, with this technology, but it is very interesting to hear that. I have one question. I know your main parameter is the emotions when you're measuring the diseases, and you found a relationship with the emotions and the disease, and so you could use this technology. But is it possible to incorporate this technology into other diseases like cancer, for instance?
Yeah, it's an interesting question. Thank you. I think we can integrate the emotional analysis every part of life, every disease, because emotions has a very strong effect on our health. So it's possible. I didn't use in any cancer research, but sure.
Thank you.
Why not?
Why not? Let's do it together then.
Yeah.
Okay, great. Thank you.
Thank you for your presentation. It was very informative. There is a question. Based on your experience in laboratory research, what would you suggest us?
I'm suggesting if you are trying to use or create a wearable device, that's you need to very familiar with the sensor systems, and maybe you can deal with the emotions, because emotion is very attractive for me. Maybe it can be attractive for you too. You can integrate the emotion every part of our life.
Okay, thank you. So if there are no further questions, I guess that was the end of this session. Thank you for sharing your invaluable knowledge with us. The next session will start at 4 p.m. and Mr. Durant will be with us. And don't forget to fill out the form shared in the chat session. Thank you again.
Thank you for having me. Have a nice day.
Okay. Hello, everyone. Firstly, I'd like to thank Mr. Akbulut for her speech. And now we are having the Professor Dominique Durand. Mr. Durand is a professor of Case Western Reserve University. He has many studies in neuroengineering. I'm passing the word to Mr. Durand to make his speech about novel form of neural communication in brain by electric field coupling. After his speech, we're going to take the questions. Yeah, you can start.
Okay, share my screen. And okay, I hope you can see that.
Yes, we do
Can you see? You can see the screen? Okay, good. So just a point of clarification, it's Case Western Reserve, not reverse. That would be a strange name. So today I'll be talking about a topic that I've been working on for quite a while, and it's getting some steam lately, and I've been keep working on it. First of all, I'd like to thank the organizers for inviting me. I will be discussing this topic of a new way that I think that neurons are talking to each other in the brain. So it's a topic that may have some important consequences, but we don't know for sure yet. But it is sure interesting to study. So here's some interesting observations. You're all familiar, I'm sure, with brain waves, and you know they are classified in these various frequencies. You probably know that they are pretty low amplitudes in the tens of microvolts, and they are everywhere, and they are in the brain, and they are thought to be too small to influence neural activity. In other words, they thought to be the result of neural activity, of the underlying neural activity, but not so much doing something on their own. And that is an area of interest, because we know that some of these waves, particularly theta waves, are involved in memory formation and consolidation, etc. So that brings the question of how is that possible? They propagate. And so these waves are not just sitting around and waiting till neuron fires to show up, but they propagate. And you can see here, there are a lot of various ways that brain waves cross the brain in different shapes. Particularly important is in the field of epilepsy, where we know there are waves there, and this is another big interest of mine. And they are being tracked. We know they propagate across the brain, on hemispheric, across the hemisphere, along the same hemisphere. They have different speeds, but basic idea is that people think that scientists believe and physicians believe that they propagate through axonal conduction and synaptic transmission, obviously. So we decided to investigate this because we observed some very strange phenomena that didn't quite fit this picture. And so we wanted to know more about this. So we built a while ago a macroelectrode array that was very novel at the time. Instead of using the Utah array that you see here on the left, which is quite big, we wanted something much smaller and to put brain slices on top of to study propagation. So we built this array out of NASA. Goddard, one of my students, went over there to build this. This is a post made of silicon, doped silicon, so it's conductive. And the top is gold. And you can see them, they're split in arrays of separated by maybe a few hundred micron across. And it's thin enough, the diameter of this is only 20 microns. So that means that the aspect ratio is really hard. 200 micron tall and 20 micron thick diameter. So we could basically put the electrode, the neural tissue on top of that, and without causing too much damage. And we were able to, you can see that we built a special chamber with electronics, which I'm not going to discuss, but the tissue will be sitting on there, but these are penetrated. They're not surface electrode, okay? So the electrode would find itself deep in the tissue, and I think I have a picture of that somewhere in there. Yeah, I'll show you that in a second, I think. So, and we also started a novel model of this propagation by studying a model of a tissue that was not done before in vitro. So what we did is I wanted to see the propagation throughout the whole hippocampus. But as you know, the hippocampus, this is a transverse section of it, is made up of several components. The CA3 dentate gyrus are connected to the CA3. The CA3 cells are connected to the CA1. And this tissue extends in a longitudinal direction. And so it's really hard to record from everything at the same time. So what I did is took this hippocampus, and what we do is we take it out entirely out of a mouse, not of a mouse, because otherwise it'd be too thick. Then we unroll the dentate gyrus, so it becomes this shape here, into a flat shape. That means we have to cut the preference path which connects the CA1 to the dentate gyrus, but that didn't bother me too much. Then we now have a flat piece of tissue, and we lay down that piece of tissue on top of the array, which is sitting right there. And I think I have a movie to show you. And what you see is these waves propagating through in 2 dimensions throughout the whole hippocampus. Let's try this again. You can see it starts in this region, septal, and goes to the temporal region. This is produced by when we put a drug called 4-aminopyridine, and which is a potassium channel blocker. And the propagation speed is always about the same, 0.1 meters per second. And if you analyze this in more detail, use now recording electrodes, different places, you can see like this one, 1, 2, and 3. You can see this wave propagating along the length of this tissue, and we can calculate the speed, and you can see here those numbers. So this is what we observe. But then if you look a bit more carefully at the literature of this phenomenon, we found something bizarre. What is strange about this is that the speed of propagation in many different situations was the same. In other words, here's an example of a preparation from the Gosselin lab. And in this case, they use magnesium, low magnesium. So if you remove magnesium or the lower magnesium, you remove the block of the glutamate receptors, and the tissue becomes very excitable. And you get seizure-like activity, you get interictal activity and they also propagate. And they propagate at 0.1 also. This is a paper by Jeffrey and Haas. And in this case, they use low calcium. We've used that too, and I've observed this many years ago, never paid attention to it. But if you remove calcium, you kill synaptic transmission. And there's no synaptic transmission, you still get activity, and that activity propagates at 0.1 meters per second, about the same. Here's another one. This one is, these two are in vitro, but this is in vivo. And in vivo, if you add carbachol, you produce artificial theta oscillations. And the speed of propagation is 0.1, same. This experiment can be done in vivo also, and you can observe cell oscillations propagating along the hippocampus in vivo. I don't have it on this table because there's too many at the same speed. So what struck me there is it's very strange that you have a mechanism that's producing a speed on, there's so many different conditions at the same value. How is that possible? So we started to investigate in more details the situation and ask ourselves, okay, how does propagation take place? And we need a form of communication between neurons for that to happen. So you have synaptic transmission, and here's an example there, right? You're familiar with this, an axon, a synapse right here releases neurotransmitter onto the neighbor, etc. So that's well known. Another one is gap junction, also not quite as well known, but still present in many tissues. It's a direct connection, a channel between two cells. So these are proteins that carry hemi-gap proteins that carry current from one cell to the next. This is a direct connection between two cells, as opposed to being a synaptic transmission that has no electrical connection. There's axonal conduction. We know axons propagate, and maybe that is what we're observing, just axons propagating. And we know there's diffusion of ions. Ions can diffuse also and generate some form of propagation. And there's another effect called electric field coupling, and also haptic coupling, where neurons produce an electric field which can influence their neighbors. So these are the ones that we know about. And we went about studying one at a time and see what's doing what. So I'll spare you a lot of details, but we blocked one at a time. We blocked gap junctions. There's a well-known blocker called mifloquine. And there's also, we can block synaptic transmission using low calcium, which I already showed you produces a wave anyway. So neither of these operations, the gap junction blocker or synaptic blockers, change the activity. The activity was still observed. You can see here the activity produced after the synaptic blocker. So this is before, this is after. You can see that the amplitude goes down, but the wave still goes on. I mean, the activity still goes on. And you compare the speed. This is spontaneous activity with no blockers, about 0.1. This is the gap junction blocker. This is synaptic blocker. They're not affecting the speed at all. So it's not gap junctions. It's not synaptic transmission. What else can it be? Well, okay, axonal conduction. Axonal conduction is a little too fast, but still possibly in the range. But it's about 0.3 to 0.5, so it's a little on the high side. And so we decided to do some experiment on that, which I'll show you later on. It cannot be diffusion because diffusion is way, way too slow. So down here is ionic diffusion. This is what we're observing. And the speed of axon is a little bit high to account for this. And so diffusion is in 4 to maybe 3 or 4 orders of magnitude lower than what we observe. And I myself measure some of these experiments, some of these speed with particularly potassium. We know there are waves of potassium passing through the brain, which are involved with migraines or spreading depression that propagate at this kind of speed. So what else is left? Well, electric field coupling. So what is that exactly? So haptic coupling is known to be the interaction by currents only between a presynaptic terminal, say like this one, and a cell. This experiment was carried out by Korn and Faber. Korn is a French scientist from Paris, and Don Faber was from Buffalo, But Don Faber, by the way, happened to be the external examiner on my PhD thesis on a completely different topic in 1980 something, two, I think. And he came to my thesis, and I knew all about his work on this hepatic, but I was not working on this at all at the time. But I remembered it when I looked at this schematic here of a soma. You see a cell, and these cells say are firing. That means there's particularly say an NMDA channel is opening. There's an inward current coming in. The current goes through the cell, comes out. So it creates a sink and the source here. The neighbors are sitting right quietly next to it, sense that, they get depolarized, and then they get right here, there's a plus, it's an outward current, passive outward current that depolarizes the dendrite. Then that current reverses because now you turn into an inward current, and then they do the same thing to their neighbor. So basically, the idea would be the electric field propagates by depolarization of neighbor cells. So that phenomenon is not known to exist. The only thing that's known to exist is this phenomenon, and that is called an FAPS, that is a small terminal affecting another cell. So we decided to investigate this in more detail, and did an experiment is what if our idea is correct, then we can formulate an hypothesis. The hypothesis is applying a field of equal and opposite strength should block propagation of activity. This is a strange experiment, but this is one that we decided to attempt because, well, if we are right, then we predict that to be true. So we took a different brain slice this time preparation. This one is called longitudinal preparation, where instead of cutting a transversely, we cut it longitudinally. So then we end up with 2 layers of neurons with dendrites as shown over here. There's very little synaptic connection there, so it makes it easier because we're only looking for the sympathetic or electric field coupling anyway. And we put an electrode here, record in the middle, and record over there. And we decided to apply an electric field in the middle. We know that these waves propagate from the temporal side to the septal side, and we could observe them in this region, and then we could stimulate here and record on the other side. And so I came up with this idea, which actually I had this idea a long time ago. This may even be my very first experiment as a professor at Case Western Reserve University. It's the idea of taking the voltage clamp, which I'm sure you're all familiar with. We take a intracellular electrode, you measure the voltage, and you apply an intracellular current to maintain that voltage. But I decided to apply the same idea extracellularly. So in other words, if I measure, so this is the voltage clamp that I was just describing, but we convert that to a clamp extracellular. So we apply an extracellular current through a resistor. This is an electrical model of the system. And so we create an extracellular voltage. We measure that through an amplifier. And then we have a differential comparator with a fixed gain, a known gain, high gain though. And then we generate a current proportional and convert that. Here's the equation that shows that we can maintain this voltage, extracellular voltage, at 0, which is the reference voltage right there, depending on the gain. So if the gain is high, right, then this voltage goes to 0. So basically, this setup taken from intracellular current can produce a 0 voltage, or we can make it 0 field, electric field outside extracellular. So here's the experiment using that setup. And what you see is the brain slice right there. You can see this propagation, the two electrodes, the amplifier, that we have a filter, a 2D converter, and computer to show the data. But basically, the recording is compared to a reference voltage. One, there's a current, just like I showed you, that applies a current right here to make sure that the voltage here is zero, always, no matter what. And so here's what happens at the electrode, at the electrode on the left side, the black one, we know that this one records the incoming activity. And you can see it there, right? It keeps going all the way through. It's about millimeter, maybe 1.2 millivolts in amplitude. These are spikes. On the red electrode, you can see the activity coming in, but at this point, at this time, when we apply the stimulus, the feedback, it stops completely and never makes it to the other side either. So basically, those spikes that are propagating from left to right are blocked right there at the site where we apply this current. And so you can see the results right here. The electrode is off, and you can see it blocked right there on the both at the red and the green electrode. Surprisingly, that experiment actually worked. So we were sort of encouraged, and we made another unbelievable prediction. Well, if it's true that electric field is responsible for this propagation, then what we have is called volume conduction. That is, the current which goes through a conductor, but through ion conduction, are carrying the propagation, not the axons. Therefore, we should be able to make a complete cut through the tissue and still observe propagation, provided the cut is not 2.5 miles long. If it's small enough, then we should still be seeing a propagation. I didn't think this was going to work, but we did the experiment anyway because that's the prediction. So here's the experiment. Take a slice, a longitudinal slice again. Here's the recording electrode. The incoming is coming from the left and going to the right. And you can see on the red electrode, another spike propagating with a delay. So clearly it's propagating same speed all the way up and down. We cut the tissue and move them far away, greater than say 400 micrometers. And you can see there's nothing on the other side. Then we take the same slice and put it back together, still cut, right? But closer together. And now all of a sudden, you see that the electrical activity is restored, passing through, and same speed. There's no change in the delay. It makes sense because propagation through the delay by volume conduction is through the speed of light, so it's instantaneous. And you can see an experiment here, the picture of the slice cut. So we can, in vitro, move the right side away or back and forth at will, which is what we did there. So that experiment really confirms that there's volume conduction. But it did it only with, say, 2 or 3 electrodes tops. So it still didn't really confirm that it was smooth propagation, although we sort of guessed it was. And we wanted to make sure that we were just not looking at synchronization between the two sides and there was a smooth transition. So what we did is we use imaging. So we use a voltage encoded, gene encoded voltage indicators. These are genes that express in transgenic mice that fluoresce depending on membrane voltage. And so you can see the slice here, and we're imaging with a CCD camera, and you can see activity starting here because at 0 time, there's nothing there. You can see activity coming through here, and then it builds up and then slowly passes on the other side. So this activity smoothly goes right through a cut. all the way up and down from the temporal to septal side. And this actually is showing the membrane voltage, not the extracellular voltage. These photons are emitted by proteins are inside the membrane, and therefore we're looking at membrane polarization. So this is a true experiment of membrane activation. So then we also predict that there should be electric field present in the cut, and you can see we measured that. And so here's just what we put 2 electrodes here, and the electric fields are dropping in the cut relative to proximal and distal side. They're in a range of about 4 millivolt per millimeter, which is pretty small, but they are there. So that means that, strangely enough, the conclusion is there is a wave that starts here on the left side, and that wave is propagating to the other side, and it's self-propagating. It's self-sustaining. In other words, the electric field generated here are strong enough to excite their neighbors all the way up and down this tissue. This is sort of a novel concept because, as I mentioned earlier, waves are not supposed to do that. Waves are only thought to be a reflection of the underlying neural activity. That clearly is not the case here. And it's sort of troubling because then you're thinking, well, if that's true, then what are the synapses doing? So the next question we asked was, well, okay, it's very nice in vitro, but is this happening in vivo? And so we did that experiment. Pretty simple. In fact, that was published recently, 2019. So here's an experiment in vivo. We take a rat this time, and the hippocampus, as you know, is organized in this direction here. We take 2 electrodes in the temporal side, 2 electrodes on the septal side. We leave enough room so we can cut in the middle, like right here. The drawing is not quite accurate. You can see a transverse section of the hippocampus. And then we add 4 epi in the temporal side right here. And then we get activity propagating, spiking activity propagating all the way up and down the hippocampus. And you can see it there before the cut. And after the cut, everything's propagating. The cut is complete, okay? Make sure that is the case. You can see that it is propagating. There's a delay between the 2 electrodes, and after the cut, it's still propagating. We do cross-correlation analysis between these electrodes, and you can see there is a small delay, time delay here, that corresponds to the correct speed. So turns out then this phenomenon also happens to be true in vivo. So here's some additional experiment. Here's some measurements of the speed. The delay and the speed correspond to about 0.1 meters per second as well. Here's a cross section of the hippocampus after the cut. You can see the entire hippocampus has been cut. So there is no basic delay between before and after the cut. So then we asked, well, if it's true that the fields that are generated by these neurons is sufficient to activate their neighbors, that means these are endogenous fields, right, so strength, then we should be able to measure it and apply our own field and produce a response with the same images. So, which is what we did. We took this is a Michigan probe, I think, and we measured 2 points, V and B. This corresponds to the dendritic region. This corresponds about to the somatic region. Distance is 100 micrometer, and here's what we observed. The field is about between 1 and 5, maybe 1 and 3 millivolt per millimeter. By the way, one millivolt per millimeter is thought to be the limit, the lowest possible, sorry, the largest possible field that can excite. Below that, you don't get any interaction. It's too small to affect neurons. So then we decided, okay, let's apply an electrode that right here, that plot a sink and a source that produce a field similar to this one, and we should be able to trigger a wave that propagates at the same speed, same conditions. And this is what this experiment showing right here. And you can see the electrode right there, right next to the slice, and we apply a current through this. It's a pulse. And you can see the trigger signal right there. You can see the waves induced by this. The shape is different, but the propagation speed is exactly the same, and it propagates the same. In other words, here's the red one and the blue one. You can see that there is propagation along the path. And we measure the speed. You can see here the red and the blue, and the speed is very similar as mentioned earlier. So basically, that hypothesis also. So we kept on going on to produce, to make prediction as to what this hypothesis entails, and testing them one after the other. And so far enough, we have not been able to disprove that hypothesis. We were interested to know what the spikes that we were generating were made of. So these spikes that we observe propagation from are NMDA dependent. Here's a cocktail made of half magnesium. So we decrease magnesium a little bit and decrease calcium a little bit for the in vitro experiments. We get these spikes. And if we add AP5, which is a known blocker of NMDA glutamate receptors, it all goes away. So we know that these spikes are involving NMDA receptors. And so we started to look into what are the mechanisms of what's going on. So our hypothesis is that propagation is generated by electric fields alone. So that means that if we build a computer model of cells that are connected by electric fields alone, then we should be able to reproduce this propagation. And that is what's shown here briefly. We published a lot. This one has been submitted and it's been published already. I forgot about mention, update that slide. What you see here is our attempt to build a computer model with 3 compartments, 1 soma and 2 dendrites. I'm only showing one here. The soma here has a lead current alone. There's no sodium channel there. The dendrite has an NMDA channel. It has a potassium channel. So here's the neurons. And these neurons are sitting right next to each other, but they're not connected by synaptic synapses, okay? Instead, they're connected only by electric fields. So in other words, these soma here is sensing the voltage just outside this dendrite, and this soma here is sensing the voltage just outside. This voltage right here is, we have developed the equation for that, the sensing the voltage generated by all the current sources and sinks from all the other compartments. So this is the sum. I'm not showing you all the equations. This is the sum of all the current sources in sync all over the model, and same here. And every other dendrite and soma gets the same thing. So the connection between these neurons is purely volume conduction. And here's a diagram of these arrays. So this is a 200 electrode array, a neuron array. It's 18 by 200. And I'm showing you here the standard way of showing this result, which is the cell number, and this is time. And so therefore that slope here is velocity of an action potential, and the color is voltage. And so what you see here is that excitation starts right here at this point, because you see a voltage propagating from cell about 30 to 200 in two directions, and it propagates in this direction. The velocity here can be calculated, obviously, the same on both sides. And you can see the propagation here clearly between cell 50, 100, and 150 from green, red, and blue. And here again, there are no synapses, okay? This is purely aphatic coupling from cell to cell. Then we simulated the idea that the experiment that we did previously, which is that where if you make a cut, you can also induce propagation through the cut. And this is what we observe as well on the computer model. You can see here a 200 micrometer cut in the side of the tissue, and you can see that clearly it's propagating. Within the cut, that green one is voltage inside the cut, electric field inside the cut, and it's smaller, but it's sufficient to excite the neighbor right after the cut. And 400 is also sufficient, but quickly after that, it stops propagating. The electric field inside the cut, as a function of distance, falls as 1 over r squared, as expected. And then we asked the question, well, if it is true for these NMDA spikes, is this also true of other waves that are not induced by our cocktail of low magnesium and lower calcium? It turns out that we didn't do this, but there is a paper from 2010 by McCormick that shows if you use a very similar concentration of calcium and magnesium, what you can do is simulate what's known as slow oscillations. That is, during sleep, we know that there are slow waves. These are observed in this particular case in the ferret visual cortex, but these waves are observed in humans as well. And so we decided to determine whether those same waves that are thought to be simulations of slow wave sleep waves are also non-synaptic, are aseptically coupled. So how do we put hippocampal slices to sleep? Well, this is shown by here. We use this very specific concentration of magnesium and calcium, and we get these waves that propagate along the hippocampus, and these are similar to what was observed in the ferret. They propagate exactly at the same speed as in the ferret, and they are, in quote, sleep waves, which are also observed in humans when they sleep. So the next question, obviously, is what are the speed of propagation? Well, you can see here the 3 electrodes reference, and this is all color coded. You can see the propagation of these waves and the speed. This is a histogram of the speed, and you can see mean value is 0.1. It goes from about 0.005 to about 0.2. So then that shows that this phenomenon is not specific to 4AP model. These sleep waves are also non-synaptic, because if we block, we'll completely remove calcium, they're still going. You can see that the orthodromic activity, which is our test of non-synaptic propagation, is this phenomenon is synaptically mediated, right? So if it goes away, that means there's no synaptic transmission. And the speed is the same, whether you have synaptic transmission or not. These sleep waves also travel through a cut, just as we showed before. You make a cut, and you can see it before the cut, after the cut. And if you put them too far away, there's nothing going on. The speed is the same. So this is all the same story. And similar to what I showed you earlier, the sleep wave also blocked by the feedback, closed loop feedback system, although we call it extracellular voltage clamp system, where the two electrodes right here are blocking the propagation. You can see it's applied right here. And at this point up to here, we see the propagation, and after that, nothing. Those black ones, still, you can see them because they're coming from the end of this tissue here. They still hit the black one, but once they hit the red one, nothing passes through. We could also, similarly, a sleep wave could be generated by an electric field. You can see that in the artifact, the trigger wave speed is the same. So it's all very, very consistent, surprising. So what is the biological significance of this? And well, we don't know for sure, but what we do know that this phenomenon exists. So for example, we know that in the brain, there are theta waves. I didn't show you the data, but we now have data obtained in vivo where we measured theta waves, and theta waves also cross a complete cut through the hippocampus. And by complete, I mean complete. We use actually a glass cover slip that is much bigger than hippocampus itself. You put the cover slip inside across the hippocampus, the propagation stops, you put it out, and it comes back again. So these theta waves are thought to be involved in encoding information, particularly place cells when the animals are walking around and they're relating their position, XYZ in a particular room, and mapping that on their hippocampus. Some cells are encoded, and that placement, that encoding is very dependent on the phase of theta. So the theta wave is like a timing signal through the hippocampus that somehow is involved in encoding this information. It's not so clear how, however. Particularly if you imagine that theta waves are produced by neural activity, by action potentials, because those action potentials would have presynaptic effects, and they may induce plasticity. So right at that time. So you don't want to have plasticity if you're encoding new information as a timer. So we think this could be, the biological significance may be memory, and there may be other aspects as well. What is the clinical relevance? One of them is the fact that surgeons and some friends of mine actually in Cleveland do that surgery in patients with epilepsy. They may cut through the hippocampus. And they claim that it works, and it does work sometimes, but many times this surgery fails, even though you cut it. So we looked more, I was talking to a neurologist, a friend of mine, and asking, well, yeah, we've just shown in the lab that if you make a cut in the hippocampus, if seizures can go through, and we have done that experiment. He says, well, that can't be right because we make a cut and we block them. So I looked more what they were doing, and it turns out they not only did they make cut, but they removed the whole head of the hippocampus, which is where seizures are started. And they also, when they make cut, they make very wide cut, much bigger than 400. So this is sort of significant. So the significance of pathological significance is that seizures can go through cuts. And by making a simple cut, you may not be able to block everything. And also, these electric fields may be involved in recruiting neurons for seizures, like seizure activity. So this could be a novel target for therapy. So I want to conclude, and I hope I've convinced you that there are ways by which electrical activity can propagate through the brain by using means that are non-synaptic. We've reproduced this in vitro. We've done it in vivo. We've done it in silico. We've been able to block them with extracellular voltage clamps. And these fields go right through a complete cut of the hippocampus. And we are continuing to study these experiments, this phenomenon, and try to find a theory to explain that now. So I want to invite you to come to see us in Cleveland. It's a beautiful spring time right now, and thank you for your time.
Thank you so much for this beautiful presentation, Mr. Duran. I have a question before the other ones, if you don't mind. Well, I don't know if you ever worked with the neural stem cells. Do you know that if there's a difference in terms of a model to work on for the propagation of the electrical field in epileptic model?
Neural stem cells, they are the early stage of development, and so we don't really work with those. We work with systems that are already developed, that are synaptically connected, that are completely formed. I don't know if you got the picture. I didn't specify, but this phenomenon really can only work, I think, in tightly coupled cells, or cells that are organized in very compactly dense networks. In other words, if you had a cell if you have a network where neurons and dendrites are all over the place, you could see that the dendrites and the soma are not lined up properly to produce this kind of propagation. And so we know that because if we take a hippocampal slice, and if you recall the experiments where we cut it, right, and the propagation goes right through, I have the data, but I didn't show it to you today. But if we slightly put them back together, shifted, where the cell layers are no longer lined up, then it no longer propagates. So you need tight alignments, which means cells that are nicely organized. And I'm pretty sure that in the neural stem cells, which are usually in culture media, studied in culture media, will not be organized in that fashion.
Thank you very much.
I hope that answers your question.
May I ask a question?
Of course.
Dominic, this was excellent talk, and it really shook me because previously I was considering epidemic as a problem of stability in neural systems. Many people do that. But now you are claiming something completely different mechanism. I never thought about this before. So I am sort of surprised. Now it seems as if there is some sort of, in case of epilepsy, according to your model, there are something wrong or something different in the way of maybe electric properties, so that such a tissue would promote the propagation of these epileptic waves. Don't you think so?
Yeah. So actually, it's deeper than that, because during sleep, you notice that all we had to do to get those waves is to change slightly the ion concentrations outside neurons. And it turns out that during sleep, that is what happens. In other words, somebody I remember a paper recently where they took measurement CSF samples during sleep of rats and mice and analyzed the ion concentrations. And they found a clear shift during sleep versus awake. And it's very possible that during sleep, sleep actually may even be caused by a change in concentrations of ions around it, which affects the activity of the network. It may, in fact, do exactly what I showed, which is produce spikes. It doesn't kill the activity, on the contrary. It produces activity, maybe even more periodic activity. So epilepsy in some ways could be involved in this process because clearly if you cut down on magnesium, you produce epileptic form activity. What my emphasis is not so much on epilepsy, although that's really what I work on, I'm interested in, but I'm interested in the general phenomenon of these electric fields and what they do, what those waves are doing in the tissue. But yes, they could very well be involved with epilepsy. And you said you were shaken by this. I hope you were not stirred.
You haven't studied myelinated cells, right?
I'm sorry, what?
Myelinated.
Myelinated. These are the tissue that we work with. Hippocampus is made of neurons, and these neurons have axons that are loosely myelinated, not like the PNS. Okay, in the PNS you have very tight, many turns of the myelin around the axons. In these neurons have not poor myelination, but they're loose and only a few turns. But anyway, these axons are cut. So, and the propagation goes right through that, so it doesn't matter too much.
Oh, it's interesting.
Thank you.
I never thought in that way. So this is quite good. I think you are up to something very, very important, and you might actually solve the problem.
We're working on that.
Very
Believe
good.
me.
Very interesting.
Thank you.
Oh. Thank you, Dominic.
Sure.
Thank you, Mr. Durant. It was very informative speech. There's a question from YouTube. Mr. Durant, what do you think about using electromagnetic field stimulation treatment? Could it as effective as electrode stimulation if we don't want to damage the structure integrity with electrodes?
Can you repeat that, please?
Okay, Mr. Durant, what do you think about using electromagnetic field stimulation treatments? Could it as effective as electrode stimulation if we don't want to damage the structure integrity with electrodes?
Oh yeah, okay. So yeah, that's a well-known phenomena. Electromagnetic stimulation does work. You can use coils. I've done a lot of work on this myself for many years. This is a technology that's on the market right now. There are many companies using this. These fields are applied externally to the brain for various conditions. One of them is depression, and it's effective. It can really help out, and it's non-invasive. There are disadvantages, however. The disadvantage is that the electric field cannot easily be controlled. So you can control the amplitude of the magnetic field. The beauty of the magnetic field is that it penetrates the brain very easily because the permeability of the brain is 1, just like air. So magnetic field goes right through. But the amount of magnetic field required to produce even a small little electric field is huge. And so you need a current in a coil outside in the range of 3,000 amps to produce threshold activation of electric fields in a range of 100 and 200 volt per meter. So there is a mismatch between the way you can apply stimulation. You need a very large amount of magnetic field to produce a very small amount of electrical activation. And it's very difficult to control what neurons are being excited. However, if there are applications where you're exciting a large number of neurons and they're known to produce beneficial effects, then it does work.
Thank you for answering the question and attending our first International Congress of BioMedTech. I hope you enjoyed the rest of the session. Thank you.
Okay, thank you.
Now we are at the end of the session. We have 15 minutes coffee break, and after that we will have Mr. Akai for his presentation. Hello, everyone. We are at the final session of this congress. We are having today Professor Dr. Metin Akay. Mr. Akay is a valuable professor that promoting biomedical education in the world by writing and editing several books. And he is a founding chair of Biomedical Engineering Department of Houston University. Now, Mr. Akay will give his presentation about biomedical engineering research and neurotechnology for brain initiatives. After his speech, we will take the questions of audiences.
Okay, thank you so much for the introduction. I'm delighted to be here, especially when I get invitation from Halil Hoca, the Professor Gülçer. I'm always ready whenever he wants me to participate in any activities in Turkey. He has been indeed an exceptional role model for many young people and many also established faculty in Turkey and also elsewhere. And I'm always amazed his depth of knowledge, of understanding of basic science, math and physics, and applied science, which is engineering. And he has also he's a man of highest ethics and unselfish person I ever known. I'm delighted to be here. And
Thank
he
you very
mentored
much
many,
for your
many
kind
people,
words, Metin.
many people, many students over the years, and this is great honor to see him this morning. So my talk is going to be on three pieces. One, as some of you may know, I was elected to serve as the president of the IEEE MBS. And the second part, I will talk about the importance of the innovation and the healthcare innovation and entrepreneurship. And the third part, I will discuss with you some of the recent research we have been doing at the University of Houston. I would like to especially encourage students to get involved in scientific societies. And today I'm talking about the oldest and the largest biomedical engineering society in the world, and which started in 1952. And the name changed from IRE to EMBS, Engineering, Medicine and Biology Society, in 1963. Membership is right now over 12,000, and we have more than 2,000 members, student members, and more than or close to 100 the countries have been participating in the activities of technical activities of IEEE MBS, and there are almost close to 100. Actually, we've surpassed the 100 student chapters and the clubs globally. Society has several well-known summer schools, and one of them, the Biocomplexity, we have been running since 2001. And actually in Turkey, Dr. Gülçer has been extremely, he was a local chair and helpful, and the Professor Dominic Duran has been also the distinguished faculty for the summer school activities. The oldest one is imaging. Actually, I had a chance to investigate when and where the summer schools started. It started in France, actually, and several mathematicians, summertime, they used to go to mountains to discuss their challenges and also the opportunities also in the field of applied mathematics and the physics also. So our society currently running almost 8. There's also one more, it's coming, 9 summer schools. And the one is this could be related to today's discussion, the neuroengineering started in Shanghai. We also sponsor several journals, and the 3 of them are actually completely owned by the IEEE MBS. Open Access Journal, as some of you may know, it's the new one, and it's really gaining a lot of attention. I believe that within 1 or 2 years, the journal will have the impact factor. I'm hoping to have very high impact to start somewhere 10. Among some of the journals right now, IEEE Journal of Biomedical and Health Informatics, impact factor is between close to 5.5 right now. And in general, we don't have very high impact factors, as you all know, for engineering journals. Transaction on medical imaging is around 10. I believe that the highest one proceedings of IEEE close to 11. We are a global society, as I indicated. We have the conferences all over the place. And this year, the conference is going to be in Guadalajara, Mexico, in a hybrid fashion. Then, hopefully, face-to-face next year, we'll be in Scotland. 2023, we will be in Sydney, Australia. 2024, we are coming back to United States, to Florida, Orlando. 2025, it's not decided, but it's going to be Northern Europe. We have several technical activities, and we are opening up these technical activities to also junior members, and they want to hear their voice, their concerns, their ideas. And I think it's going to be very important for our society for future. Society has several chapter awards. I strongly encourage the Biruni University to consider building a club or chapters, and it's going to be, there's also every year we honor one or two societies based on their contributions. And also we have the regional chapter awards for the areas. Last year, these are the winners 2020, and for different part of it and of the world and the countries. Society has the EMBS IEEE fellow is very unique, very different than many fellow positions. In fact, the selection rate is based on our society size, and it's highly prestigious, is less than or close to 1% of the members. When I elected as a president, I would like to share some of the vision, and this is the IEEE MBS. The office was very kind and prepared. Actually, as of today, we received is more than close to 14,000 people actually viewed this division statement. It's remarkable, assuming that we have only 12,000 members. The first and most important thing to me is to really honor the contribution of the woman in the society. Women should be ahead of our society, our economy, everything. When you have the woman, which means that you have the peace. So I'm extremely dedicated to promote the women, female scientists and engineering, by really encouraging them involved with our conferences, publication, technical activities. It's not just attending. I would like to see our administrative council should have at least half of them females, and I want to see half of the keynote speaker would be a woman, and I would like to really do everything to promote them. And it's they have been contributing to our society. They have played incredible role for decades, actually, since 1950s. The second, the mission was, I decided, I mean, with the help of my colleagues, actually, let me use the word, we decided to have public forums, which means that is the highlight certain pressing the healthcare issues, and the free of charge for whole community open up with the participation of the distinguished speakers. The first one we had, my bias is, I believe that we have organized one of the most comprehensive COVID-19 forum, and the 4 days, and in 4 different areas, including the healthcare, screening, tracing, and treatment, and it was open to public. We had online, close to 800 people attended, and it's also, we are going to prepare the presentation, and it's going to be documentary actually, and we are hoping that one of the leading outlets will use it. So the second, the part is going to be also the point of care diagnostic conference, which will be held in Houston. We will continue having the forum as a part of this conference. The second initiative I had, public forum, data science and engineering. This was also remarkable. Close to 2,000 people attended. So for this one also, we have 36 the keynote speakers, and in 4 different areas: medical imaging, digital health, precision medicine, brain and nervous system. Initially, I envisioned to have it in Israel jointly with Technion, and because of the pandemics, we end up canceling it. That's we have hybrid, and hopefully next year we are going to have it in either in Israel or in Italy, Capri Island, and again it's going to be hybrid format for this. So for data science is for each section we had the total of 8 the area or the team chairs, and they are listed, and still students are welcome to check the related web pages. So the third one I'm going to do this summer is as a president, I also envision to have the healthcare leaders, influencer, and entrepreneurs forum. This is going to be again 4 days, 4 different areas, and they hope to have 24 speakers, because most of the societies, our society, we have exceptional the speakers, they come, but we never had really open discussion and they involve the junior students and junior colleagues with part of it. So this is not just only listen their challenges and opportunities, also to allow the students and the junior faculty bring some ideas to the forum, and they that had the pitch for this. So this is not, as you can see, still is fluid, but the vision is behind. We have to get industry, healthcare industry leaders involved with our society. And I assure you, they will. I also started the new program is the Presidential Distinguished Lecturer. These are the industry leaders. And in addition to our existing exceptional distinguished lecture program, and we are limiting the number. I have 7 people, and from Erica, from the Abbott Neuromodulation, the group directors, and is Eva. She gave an amazing talk at the COVID-19 forum. She's a CEO of the Trinova from Europe, and the company focus on more the CT, advanced CT system with the AI for the detection of the COVID-19. And Anita from the HB Lab, she's the leader for the life science group, and Natalie, she's the CEO of the Prof US, and she has been amazing the entrepreneurs for over the years. Did you notice something? All those leaders are females, actually. So far, okay. Dr. Renita Binoska, also she's leading the computational biology group at the Pfizer's, and Alit Nazlı is a German American, and the 3-4 generation they are from Germany. He was the head of the Sony Bio, and then became the global head of the HP. Right now, he is the CEO of the Flux Energy. Mike, as some of you may know very well, is with the vice president for the Medtronic. So this group of the speakers, I will start the webinars this summer, and will be available for the ITIL PMBS chapters to invitation. I think it's going to be very important to get them involved. Okay, the importance of the healthcare entrepreneurship, the second part. This is the slides maybe I used many times in the past. This I borrowed from World Health Organization. Is which kind of disease we are going to face next decades. This starts from early 2000 and goes all the way 2030. We are almost there, right? If you look at the top 4 diseases, are all chronic disease. Of course, you don't see COVID-19 in the table, but I think it's sort of hidden in a way that is a chronic disease, and the respiratory-related disease, brain-related disease. COVID is all over the place in the table, because Also, there is a significant increase in cancer incidence. Cancer is a global disease right now. Cancer is an immune disease, and COVID-19 also is an immune disease as well. And the third one is significant investment in the research in neuro, and also significant increase in the neurological disease. Of course, the neuro-related disease goes almost 2000 before the early part of the Chinese dynasty, actually. We are talking about the first neurosurgeons, about the epilepsy, who was hoping to treat the Chinese emperor. And there's a very interesting books that those who visited and who may visit the Taiwan National Museum, you will see the almost textbook for neuroscience, and at least what I looked at from the distance, it seems that it almost reminds me any good neuroscience books these days. BME still is the growing discipline all over the place. These are the numbers, but the focus is significantly shifted. I'm a department chair at the University of Houston, and this year, close to 50% of our students, they have jobs in the areas of data science in healthcare. It's remarkable. And this was projected because many meetings that is Dominic and I organized, and we gave lectures globally, we could see that trends is at least last decade to me. But this will be more job openings in these areas, and expected numbers is varying with journals and which magazine you read it, somewhere from 100% to 300% job openings in that area. And also the moving into the more micro nano for neurotechnology, and also for the drug design, drug treatment will be the future of in my view, humble view, for biomedical engineering. So these are the numbers. Tom Skalak and myself, we organized the engineering summit, actually, I called it is. We were looking for how much money has been spent. Of course, I revised the PowerPoint. These numbers on screen right now is the 2017, 2018. In the US, the spending, research spending in the areas of bioengineering, we were talking about more than $1 trillion, which is much higher than many countries' GDP. Most of the spendings actually is close to $1 trillion in the areas of biopharma engineering and science. Of course, at least the US government and European government, I'm sure that some Asian, China, they vastly invested for the vaccine development. Those numbers are not included. And I also believe that is the biomedical science and engineering, they significantly promote the vaccine development. Of course, with the medicine. So for the medical devices, if you look at them, $500 billion we are talking about, still orthopedic device technologies gets the lion's share. Then cardiovascular, neuro is still, as of today, number 3. But I'm sure that is Dominic and the Gulcher will agree with me that is within a decade, neurotechnology will come close to cardio, may surpass the cardiology. Okay. When I go back to, of course, the vaccines were designed by the scientists and some of the medical doctors also, as you know, but I think the science and the engineering actually, they played a key role for the vaccine development. Let me correct that. This is the GDP. This is the 2015 old number. I think is right now China is increased, and we are talking about the US close to $20 trillion. If you look at India, it was $2 trillion, and Italy very close to $2 trillion. In between these two countries, I don't want to call the country, but the institution is also contributes to global economy as much as any country's GDP. This institution is called Massachusetts Institute of Technology. Their contribution to economy, we are talking about 2016, 2017, is almost $2 trillion. The reason for this, the innovations. How you translate the ideas into the product and also change the whole ecosystem and culture. Focus on is the critical thinking and the translation, with having the academic freedom, of course. So they have built, the graduates of the MIT built more than 30,000 companies. They hired close to 5 million people, and they contribute to, so these are from the MIT and the media. This is the University of Houston. I will go to a little bit talk about the ecosystem in Houston. I was invited to give a talk 2009, accepted the job 2010 to build completely brand new biomedical engineering department. So this is our building, the second floor. Of course, if you look at the building, every floor there is something related to bio. Definitely, we were located at the right place, and we started to building. Actually, it took a little bit time at the beginning for every jobs, for every new initiatives. I think the building has close to 140,000 square foot space, and our department is right now expanded from the only 1 floor, 1.5 floor to the other buildings, and our number also significantly increased. So just a couple the notes for the students. I mean, it's of course need to focus on the new technologies, new areas, developing areas, challenging areas. But what matters for it will be very important to have a very strong analytical skills. The communications in general may be the weakest spot some of the engineering students, but I think we need to focus on. It's very important we have to relay our mission to the public. The public is, be honest with you, they're very smart people. But we need to be in a way that to present the importance and significance of our research. Of course, leadership, creativity, and I strongly encourage the students go have an internship to also go listen different talks from different departments, open your horizon. I think it's a good example. We need to be a little bit more Marco Polo. I mean, it's just some ideas in physics and mathematics or chemistry or elsewhere could really help to engineers to resolve some of the important, the challenging struggles ahead of us. For our department at Houston, we have 3 areas: the neurocognitive rehabilitation, the one, then second, the bioneuroscience. I also believe that we may be one of the first or among the first departments hire the immunologists. Actually, I hired is an MD, PhD, and the 2 of them. It was amazing that how much these 2 Professor Mohan and the Professor Wu, starting from immunology and the embracing the technologies, and to my best knowledge is they may be one of the most heavily funded faculty. Mohan maybe has the 4 NIH R01s, and I have also faculty with 6 R01, 3 leading PIs and the 3 co-PIs on this. The third one, if you look at the name, is biomedical imaging informatics. Soon we are going to change into data science and engineering in healthcare. This is Houston, is the largest medical complex in the world. This number may not be perfectly correct, but I believe that we have close to 37 hospitals in that area. And some of the hospital names, I'm sure you're very familiar. MD Anderson, for example, has several hospitals, is leading the cancer institutes. And there's also incredible shift in addition to the exceptional service, and the ecosystem is focusing on more healthcare entrepreneurship and also innovations. Baylor College of Medicine, we have 3 medical schools, actually 4 right now. University of Houston started the new medical school, and I received incredible help, actually, multiple people, and one of them is our Chancellor, Jenny Kator. She envisioned also having the medical school is more community-based medical school. So it also opens up the health, because the many communicable disease and the community-related healthcare activities indeed require the engineering innovations. Our medical school is uniquely different, and also she was able to get the donations. And in the United States, most of the medical schools, they pay for the tuitions. So the University of Houston Medical School, they have the fellowships to cover all the students' fellowship as of today. And other hospitals, Baylor College of Medicine, Rice University is one of the leading private the university, one of the well-respected university. UT Health, another well-respected the healthcare, health science, the university. Also, Memorial Hermann Hospitals, and UT Galveston has the infectious disease-based medical school. I had a chance to visit there. I believe that is one of the well-respected, maybe the largest infectious disease, the facilities. And that time, I recall that at least the 4 BSL 4 level 2, the labs, they had the systems. So I think the system is there, and the fantastic universities, University of Houston, Rice, Texas A&M, also some activities, as you can see, UT Health, and it's create enormous the population of almost like 150,000 patients. They come to Texas Medical Center. 150,000 medical doctors, healthcare providers, nurses, and ours also. So we are talking about 300,000 the population, a small city. This biotech and farm cluster in the US is really, this needs also a little bit updated. Anne, she's our industry advisory board member. She was very kind, allowed me to share the slides. I am also closely watching what's going on with the biotech industry. And since the topic of the BioMed, the technology of the conference, organized by the Brunel University, let me talk about the ecosystem in Houston and outside a little bit. For San Francisco, in fact, the 53% of our PhDs, they have received jobs, they accepted the jobs in California area. San Diego and LA is completely merged right now. And if you drive between them, you will see the companies around right and left. It's an amazing area for not only healthcare technologies, but also data science technologies. And San Francisco also, in addition to the IT technology, I think it's the healthcare technology is booming. Northeast is always the Boston area, as you know, is the exceptional universities, and they are really innovating, translating, building their own companies. Houston is the last 10 years, not only Houston, but also Austin is coming up too. Right now is more than 300 as of today, life science, medical device, and digital health companies in the area of Houston. So it's very diverse, as I mentioned, all these three of them are mixed. So every stage of the company, even Johnson & Johnson Innovation, they have a large activities in Houston. So this creates the very healthy platform for our students to have capstone project, to have internship, and also the possibility of the jobs. Our faculty, at least in my department, 3 out of 18 professors, they have their own companies right now. I'm encouraging them, and because they build companies with their students, this encouragement coming from our every level of administration, my chancellor, Kator, provost, Schott, and the Dean Tedesco, every level, we are encouraging the innovation at University of Houston. And this is also, at our university, we have a dedicated space for the companies, and it's almost the Innova facilities. I think I recall that is Professor Gütcher was leading, actually. He may be one of the first, actually, in Turkey, promoting the idea of building companies. I think it's I visited a few places with him. These are the very important for not only our students and also the local economy. Let me go to the little bit the neurotechnology part. It's always challenging to give a talk after Professor Dominic Duran. I'm sure that he covered many areas. I will do my best not to focus on the same areas. The brain implants is the first was developed and they actually implanted it at the University of the Pennsylvania. After a couple months later, the patient requested the implants to be removed. To me, the most fascinating still is the one that developed the Brown Group, and right now they have the couple companies and some of the leadership they moved to Wyss Institute in Switzerland right now. The implants this is a typical in silicon. The implants and the Utah array, and the whole idea is to really record the brain activity, which is a continuous activity. Even during the sleep, our brain is one of the most active organs. The active, maybe. Okay. But the recording is a challenge because if you look at each part of the brain, they have different types of the neurons. Their soma is different, their axons are different, and so the design of the electrodes to record one size may not fit to all. So if you look at this is for the somacenter area, and these are the metal electrodes, and the old version recording from monkey's brain, as you can see, single unit recording, and they open the skull and they place the recording unit to the brain. But if you look at them, most of the activities are above the skull and also requires battery, all this multiplexing, pre-processing, and we are talking about the milliwatt level power consumptions. When you look at the right-hand side, monkey is trying to move and touch the food outside. As you can see, it's getting closer and the more neural firing is happening. I'm not saying that is by looking on the single units, we can predict the monkey's behavior, but at least there's a relation. We may go even from single gene to all the way behavior. That was the concept of the summer school we have been organizing many years. Regardless, the device, the technology at the left-hand side were archaic and should be in the Smithsonian Museum, and the group moved into the more the compact and the completely implantable, the wireless neural microsystems. As you can see, multi-electrodes are placed above the brain, and also there is a wires coming through the dura, and there's a cranial units is telemetry. Power comes, inductive power, no battery, and they pump the data out, they get the energy in. And outside is the small piece, and even someone sits on the airplane next to you, you may not know that person has this. We'll talk about our research in the lab. One of the research areas in our lab, we are very much interested to understanding of the addiction. So this is almost we have spent almost 2 decades on this research. We are working on the project in multiple level, at the genomics level and also cellular level, and moving into the behavioral level. VTA is a very unique, and it's related in the midbrain. The size is almost like oval shape or sizeless. It's more challenging to do recording from VTA compared to the cortex. And also the VTA, if you look at the projects, the dopaminergic projection to prefrontal cortex, the axons is maybe very long compared to the many parts of the brain. There's also projection from NAC and other part, and the network is basically VTA is significant number of the dopamine neurons are located in VTA. When there is an excitement, this excitement could be, for example, Fenerbahce becomes champion, and most of these neurons becomes active, fires, and then or Beşiktaş becomes champions. I'm sorry, and the projects the prefrontal cortex and the dopamine release into the systems, and it's almost like you're driving the car, you press the gas. And the brake is coming from GABA and the projection coming back to NAC and also VTA. So the system is seems to be, this is not too simple as I indicated, but is a challenging because the addiction has been the world problem right now. So our idea, our concept is to first understand the mechanism, know where the neurons are located, understand their behavior at many scale, many level, and then develop therapeutics. So dopamine neurons is unique. Even when we look at the activities, I'm going to go to the directly if I have. Okay. So difference between the dopamine neuron and GABA, even if you look at the waveform, is the GABA seems to be more fast varying and compared to dopamine neurons. How do we get the data? So this is the animal model, rat and mice, we use it. And we open nanoholes, and as you can see, to reach the VTA. And we have a model is based on the developmental and the anatomic structures. And we know where to go, and we push the electrodes to reach the area. So the area is we are talking about 1 millimeter, no more than. I will show you a couple of pictures. Of course, the old traditional ways, we were using the wire electrodes, and then we are recording from the single units. Then we move into we use the neural nexus electrodes. Right now, it's not published, but I'm going to share some of the new initiatives from our groups. So to analysis, when we recorded, we are looking before, during, and after nicotine administration. And then we are looking for the activities. In this case, I'm sure that many of you are very familiar, LZ approach has been used, and this has been used many different, it's almost like the pulse train. You're looking for the number of the motifs, number of the patterns in the pulse train. So it's simply the convert them into the 0 and 1 binary, and don't repeat the same patterns, and then estimate the number of the words, number of the patterns, and just come up with the one number. But be honest with you, forget about this analysis modeling part. When I look at this simple, before and after nicotine injection, from only one dopamine neuron located in VTA, upper panel shows before the nicotine, lower panel after nicotine injection. As you can see that there's a significant increase in the neural activity after nicotine administration. So nicotine is a stimulant, alcohol is a stimulant, cocaine is a stimulant, all of them, they create more or less the same patterns. So when we look at them, how much the changes, the black one is the before nicotine, and after the nicotine, as you can see, and it's significant increase in LZ complexity. When we cut the connection between VTA and PFC, and we don't see that changes, then we move into the record from multi-channel activities, multi-recording areas. I want to acknowledge the contribution here. These recordings were done by Dr. Dia Zhang, and most of the analysis were done by Dr. Andre Dragomir. So we are trying to look at not the neurons, multiple neurons, and also to locate our electrode arrays, somewhere starting from 0.5 millimeter to all the way 1.1 millimeter. So if you look at anatomical structure, PBP is the top part of the VTA, and then PIF and the PN. And our goal first to understand where they are located, and then also to quantify the neural activity. Our data using the different analysis methods, I don't want to go details, and some signal processing, including the wavelets, and we have used the several biocomplex methods. I just want to reiterate here. These biocomplex methods just signal processing methods. They do not really reflect the anatomical biocomplexity. So when we look at the difference, saline versus nicotine, most of the changes activities in the areas of PIF and also some part of the PN. So this indicates that large population of the dopamine neurons are in these two areas. This may be one of the first papers that try to quantify using electrophysiology and eventually using also the gene expression. We have several papers published, Nature Scientific Reports and elsewhere, and this has been highlighted by the AAAS and the Science Daily also, was the show the influence of prenatal alcohol take by mother influence on the babies we are focusing on right now. To look at the more maturation of the effect of nicotine and alcohol and mix both of them on the development. That's the goal. So we moved and we look at them to model in a more sophisticated method, and I'm sure that all the engineers are very familiar with the gamma distribution. When you look at there's a one defining parameter is the firing irregularity parameters. When you look at the burst type activity, K is smaller, comes close to 0 is the burst type activity, and then K is 1 is the random, and K is the larger than 1 is the regular. In fact, these three firing patterns are indeed exactly how the dopamine neurons firing in VTA. The burst type is more release of the dopamine to the PFC, and the random and also the regular, the random is a transition and regular is the normal one. So therefore, when we look at the firing irregularity of the burst type, and as you can see, the irregularity parameters is around 0.75, and for transition, random firing is not really the straight, is going down with the time, and the continuous one is the much higher. And when we compare to FFT-based systems, of course, the FFT is very useful, gives some initial idea, but it was not more resilient as much as the firing patterns. We modeled the whole system in the 3 states, and the continuous firing, low SO, and the high SO firing, and the 3 states, but the 3 unique the firing patterns condition. Here is a very exciting result. The high SO is in the burst type activity. After nicotine administration, the duration of the brain or VTA in that mode significantly increased and compared to low and continuous. So it's basically what I'm saying, that is, if we give saline, high SO, which is the burst type activity, which is the dopamine release, is much less compared to transition and continuous one. After nicotine injection is the duration and staying in the burst type activity significantly increase. This may be among the first studies actually pointing out that is the modeling based using the Markov process, and it was very, very helpful. The problem is then the single unit recording, and we move into something very unique. This is a joint work with the Professor Ota. We have been working together almost 10 years, and Sunaga is the postdoc that works with Dr. Akai and myself. Instead of recording single units, we have developed is the implantable CMOS-based microimaging systems. So we want to image the whole VTA area. We are talking about the size 0.3 millimeters to 0.6 millimeters. It's almost perfectly fits the area of the VTA. So these are of course, we are looking for the fluorescence imaging, and the initial studies I'm going to share with you. It is completely implementable, and also damage to tissue is not too high. We are talking about when we inserted, we were able to get the 50, 60 micrometer area is damaged, but still the sensing capacity is very high. Let me repeat one more time. It's a joint effort, Ota and Akai group, and the Japan and the United States. So right now we move into not only imaging, we are also putting the recording sites to get the electrophysiology right and left. So we will record at the same time from thousands, hundreds of thousands neurons, and also the extracellular activities. So this is the early part, it was published in IEEE Access. And also this is another EMBS co-sponsored. I think impact factor is coming close to 5 right now with that one. And this is the whole VTA, and this is our one let, not two. As you can see, that is the activities, we can image the whole area. I cannot tell how many neurons are there, but I can tell that is the activity-wise, we can quantify, we can link them. To get the fluorescence image, we have to give these are not the .cray animals, and you need to give the GCAM virus needs to be injected 2 weeks before the activities. We are moving into the more sophisticated one, and to get this, and also we are right now stimulating the area. These are the, again, is a joint work with the OHTA groups. We have also the Plaxons of the genetics. So in addition to nicotine, alcohol, we are using right now the optogenetics to look at the dopamine release in PFC. So we can stimulate, we can look at the neural activities in VTA, and also we can quantify, measure, quantify the amount of the dopamine release in PFC. And also we are going to do NAC as well. So these are some of the early studies. As you can see, the dopamine release in PFC, NAC, and it takes time to really to get the, I mean, for the PFC it takes the 30 minutes. Again, we are using the traditionally, commercially available, the microdialysis system. The resolution is not perfect. So you need almost the 10 to 15 minutes to really extract the liquid and determine the quantity of the dopamine. And we are going to explore and the new novel technologies for the detection of the dopamine in PFC, and maybe collaborate with the colleagues who have the technologies with us. And it's the interesting part, if you look at the NAC, which is very close to VTA, and the dopamine release, it takes more time to have the high dopamine release. So distance does not mean that larger effect. That's also very interesting. So these are again the other studies, and the nicotine and alcohol, and we are also working the new design, and we are going to stimulate each area separately, measure, quantify the also dopamine release. So our new technology is the 3 stimulus point we have it. I think it's going to be exciting to look at them. Hopefully next time when I have the chance to present, and I will talk about this. Okay, so what we need to done, and the biggest challenge, I think, even I recall that one of the meetings that Dominic brought it up, it's the recording sites we are doing very well. I think that it's important to connection part. I mean, the connection part I'm talking about after this, the recording, imaging recording is with the animals, the free moving animals. So for them is having so much wires, and the connector part are real challenge. So eventually we need to look more and more to have the wireless systems. Although the animal is not really the mouse in our case in the cage, it's free moving, but it's not really the free moving, and it's the control. So the one area that we are interested to again to look at even the microdialysis part, and also the optogenetics part, to have the more fully implantable compact technologies for this. Okay, so let me go back to, I think the issue is the problem cannot be understood easily if you look at only one part of the pictures. I think we need to look at from the genomic side, which is very important. Right now is we are looking for microRNA, mRNA interaction also during the alcohol nicotine injection, after alcohol nicotine injection. And also we are using machine learning techniques actually to understand the gene pathways. And soon we are going to have 2 papers will be published on this. And the same animal, we right now moving into the look at the more electrophysiology and behavior part is coming in this. Okay. There's another unrelated research is the brain chip we have developed in our lab, which was actually the highlights of the, it was published in the Open Access Journal. And the last July, our paper was the number 2 out of 5.3 million papers ever published with IEEE, download-wise and also interactions. I think that was also the over thousands news outlets shared globally, including newspapers and others. I don't know how many million people had an access, indeed access, because they, I had a pleasure to look at the several international journals also they were at work. So idea is behind, it's almost the, I was born in eastern part of the Turkey in the Sivas, and the Selçuk Turks, they were great to build the, it's called hammam, it's also sauna. There's always the corners, the release points, and in the center, you have the center of the pool. So the challenge for GBM, life expectancy is too short. It's very challenging to keep using the more chemotherapy drugs because we don't know which one works which patient. So the concept, I had no clue. I was at the, one of the conference in Europe on the cancer-related conference. And after listening to our conversation, I suggested that why not to use a technology like almost cell phone, get the samples from hospital, and then put them in, inside the microvalves. These are all developed by our group. And then use the different drugs for different corner. Mathematically, we can figure out that is which one is in the, they may have a better picture. Okay, which one may have the, we can determine the concentration of the drugs inside each microvalve, which we have the patient A sample. By looking for the effect of the drug on hundreds, the microvalves, we can determine that is which combination the kills the or the shrinks the spheroids more. It was very effective. Actually, these are 3 people, they did the work. In center, Dr. Akai, Dr. Avcı at the left, and the Dr. Shia at the other side. And it's the, we are currently using with our colleagues at the Texas Medical Center. These are the technologies, and I think I'm gonna, it's almost time is coming. I'm gonna stop here, and thank you so much for listening to my talk. Thanks for the wonderful, the inviting me to a wonderful symposium. Dominic, great to see you, Professor Gülçer, and I'm always grateful to you. Okay, let me stop here. I'm open to questions, and if any.
Thank you for Mr. Alkay for that wonderful speech. There's a question. What was the main reason got you interested in neuroscience?
Neuroscience?
Yeah,
I think I mean, be honest with you, every research is important at every level. I think the neuroscience is, I would like to mention that I was, Dominic actually is more senior than me. I think, I read his paper and the principal papers, and I read the several papers early on when I was in Istanbul. It was really fascinated to see the neural firing, and the early papers, the analysis of EEG was really the important. And the second is, still I believe that is, there are much more challenging research questions in neuroscience. For example, in our case, the accessing VTA. I mean, this presentation is like 45 minutes, 50 minutes. If you look at the Dr. Dominic Duran's the presentation, 45 minutes, I can assure you that is there is 45 hours, there are years of the energy and time to this. And the cardio is compared to neuro, and we know more about the cardiovascular system. But they are all linked to each other. Again, they're all important areas. And even the, for example, the COVID-19, when we had the Dr. Boskurt and also Christy Wong, and they are the two leading experts in cardiology and brain, they were talking about the COVID-19 influence on the heart and the brain. And we are talking about respiratory connection to cardio and brain. They're all linked.
Thank you for
And
answering the question.
Second part of the answer is, look at, if we did not live too long, life expectancy was very short, okay? So if you look at the life expectancy right now in developed countries, we are talking about 83, 85, and in Europe also more or less the same. And so the certain neurological disease, we did not face Alzheimer's disease, for example, or many others, because we didn't live too long. And so more and more we are dealing dementia and many other neurological disease because of we live longer. But good news is, engineers, I think we are innovators. I think the contribution of engineers and scientists are, in fact, significantly helping to medical technology. Of course, the prices are still high for the technologies, but also quality is getting better and better. I think we need to focus on more how to reduce the cost of this too. Okay, thank you.
Metin Hocam, thank you very much.
Thank you.
Thank you very much for your kind acceptance for our Congress. It was very nice meeting you, by the way. For your first part of presentation, I'm sure it was very inspiring for all of our students who be the part of the biomedical engineering field globally. Do you have any internship options for our students for the summer, for the winter?
Okay, so because of the pandemics, I will say that I need to be honest with you, I was remotely working. And in our lab, we had only 2 or 3 students, they were doing the research because of social distancing. And so we did not have so many applications. I mean, I don't want to say, we were unable to really accommodate anybody from outside because we were unable to accommodate our own students. So mainly we had the graduate students working, and depends on what will happen. I'm a very optimistic person. And I believe that is mankind, we are, look at the Turkish history, right? The reason that Turkish state and the republic will live forever, I know, because we adapted fast. I think we will confine the virus as a global community. We will, things will get better. And that time, I think the opportunities will arise. Okay.
Thank you very much.
One advantage we have is the medical center. And I really hope that many BME department, I'm sure that Dominic would agree with me, that have more, the internship should be with the medical industry. So the student, they have to see, because 80%, 90%, they get the job at the industry early on. We need to push them. They have to be critical thinker, open-minded, early on. I'm talking about freshman level when they come. I think never underestimate the young people, and I have full faith on them.
Well, cannot wait to COVID to be over.
Yes,
so
I hope so.
We meet maybe face to face in the future.
Thank you. Go ahead,
maybe I will ask a quick question. Thank you very much for your inspiring and really amazing and deep presentation. A quick question.
Yeah.
What do you think of Elon Musk's neural link project?
Okay. I think I have respect the people, they have the novel idea, good idea. I think there are several similar projects. I don't want to mention his name, his group, because I have colleagues working in that group. And since we were, I don't want to call that, we were heavily involved with the neural engineering conferences late 1990s. So the goal should be help the people suffering from neurological disease. That could be at least our humble goal for this. So the enhancing the memory should be for Alzheimer's patients disease. So priority. So I think it's the it will be nice to watch, and any contribution to the field of neural engineering highly appreciated. But at least my personal view, these technologies should be developed to help the people's well-being. I think this is a little bit political answer, but I think you got the message.
We got the message. Thank you. Well, on behalf of Biruni University, we would like to thank.
Can I ask a quick question?
Yeah, please, Dominic, go ahead, please.
Sorry.
Dominic.
Yeah, I like the what you're doing with the imaging, but the VTA is in the brainstem, and you're putting this device in there. Doesn't that cause significant damage? Actually, dangerous possibility of damaging the.
Yeah, Dominic, I think we may be a few people that when we present this work, this was really the. I always present. I don't have the images that I also show the tissue damage. We did extensive work. We have shown that is the damage is to the surface. We are talking about 50 micrometers area is damaged, much less than, be honest with you, many implantable arrays and developed by other colleagues. So we were fine with that one. 50 micrometers as an expert, I think you also appreciate on this.
Yeah, no, just want further this question though. 50 micrometers, okay, but let's say you're pushing this device into the brainstem. The brainstem is very sensitive area.
Yeah.
And controls many parts of the body. So what's the yield of these experiments?
Fantastic.
Really?
Answer, I'll be honest with you. I'm going to have, I don't want to say breakthroughs very soon about the 7 days, 14 days, 21 days pups. Just wait.
Okay, all right.
I mean, it's just wait means that maybe 10 years, Dominic.
I know. I've been there, done that.
I know, but you have been a pioneering person. I know how patient you are. What you have developed also greatly appreciated, Dominic. And you have been a great role model for all of us. Thank you. Okay.
If there's no other question, on the behalf of Biruni University, I would like to thank all of our speakers for your very beautiful speech and inspiring talk for our students. Well, I hope to see you soon.
Thank you. Thank you
in the future, face to face. Thank you.
Thank you. Have a nice day. Thank you.
Bye,
Just
Metin. Say hi to Yasmin.
before closing, Metin, how about, and Dominic, how about organizing a very big meeting on Alzheimer's in Istanbul?
Actually, I don't have expertise, and Dominic is there. I can help.
I don't have any expertise either. Sorry.
Okay, but I think that.
No, but
okay.
You see, you have to bring together all the experts.
Okay.
So that
here's my humble suggestion.
Some solution.
I think it's more than Alzheimer. I think the most important issue right now is the mental disease. Okay, I think it's the mental disease it's the reported part. We are talking about 500 million people globally right now. They suffer mental related disease. Out of 6-7 billions. Incredible amount. So I think is the issue is right now, because also the depression and other things, they're all, of course, involved with the Alzheimer's is very important too. We could mobilize some colleagues from UCLA, USC, or Berkeley group. They could have a section, but I think the major problem, if you ask my opinion, next decade we will face the mental problem. Mental problem is leading for the addiction, mental problem causing many other issues, and also many suicides.
Sure.
I have to go, guys.
Okay. Enjoy your day, Dominic. And
thanks.
Say hi.
Nice to hear from you.
Thank you very much. Thank you very much.
Have a great time. Goodbye.
Thank you.
Nice to meet you.
Bye.
İyi günler. Bye.
İyi günler.